Oh, you could add a street marker. It's pretty good, actually. I don't like how that thing is blocking the whole entire chat. How do I get rid of it? Here, this. Doesn't go away, I guess, until... Okay, I see. Hmm. Okay. Okay, there we go. I don't know why. The way they word that is terrible. Wait, what? Why is it 31? Oh, because 32 is the next, Wait, what? Mm, 16 subnets? Subnetting a network address 172.30.00/16. Okay, so calculate how many subnets are required, then round up to the nearest power of 2. So let's say we need 12 subnets. So 12 subnets, so the next closest is going to be 16. Exponent is the number of bits needed, so 2 to the 4 is 16. So you're going to add 4 bits to the mask. So it's already /16, so it's 255, 255, and then you want 4, which is going to be the 4 less than 255, which is going to be, it's 255, then this is 256, why is it 255? Oh, because it starts at 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 4, 8, 16, 32, 128. Added all together is what? 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. Oh, it's 255. So where's 256 come in? So add 4 bits, so that's going to be 1, 2, 3, 4 is equal to 240, because 1 is going to be 128, 2 is going to be 192, and that's because of, I worked it out yesterday during the quiz, and then I forgot how I did that, somehow. I just brute forced logic through it. Hmm. 2 to the 4 is 16. Oh, so it would be just 256 minus 16, which would be 240. Because if it's all ones, it's 255. Wait a minute. I see. Wait, no, I don't see. Oh, I do see, because it has to be consecutive ones coming from the left. Wait. So if it's a 1, huh? Hold on. So if it's a 1, what's 256 minus 128? Is 128, right? And then you subtract the 64 from that. 64. Wait, yeah. Wait, so how do you get 192? Minus 64 is 182? Okay. So then minus 32 is that. Okay, now I'm getting somewhere. Now I'm starting to... So... How is 1 bit 128 though? I don't understand. 1 bit is not 128. 1 bit, it would be 1. No, it wouldn't be. It would be 1. Oh, I see. I see. I see. Because you have to line it up with the placeholders. So really it's if it's just 1 bit starting all the way at the end, it's 128 because it's 128, 64, 32, 16. So you just add those up. So if it's 128, wait a minute. No, that doesn't even make any sense. Yeah, first one, would that make sense? But that no, I'm thinking it the wrong way. Because if it's the 1, it's 128. So then you just add 128. Now let's say you got 2 placeholders. It's 128 and 64. So 128 plus 64 is 192. Oh. And then you want to add 32. Yeah, that's 224. And you want to add 16. Oops. 16 is 240. Yeah, that makes more sense. It's easiest when you start doing base 2 calculations, when you think of it in base 2, because then it's like you're less abstracting. The more, once you start abstracting, then it starts to get confusing. And you can't see that, but you can see half of it. Okay, so if you need 12 subnets, then we need to figure out how many bits we need to allocate to fit 12 subnets. So you want to allocate 1 bit, which would allow for oh, that's because it's starting at 2 to the 2, but if it's 2 to the 1, then it would be just 2. I not? No, it just started like that. Weird. But technically, this can have like a whole. How do I? Here. Now I can do it. Now I could add like 2 to the 1. Just kind of even it out more, line it up better. So if you only need 2 subnets, if you just want to split it in half, it'll be 2 to the 1, which means you just add 1 bit. And so that'll give you 128. So then it would be 172.130.128.0 is the second subnet, and the first one would just be 00. Yeah. Is that how that works? No. So let's see. Let's keep going through here. So calculate how many hosts. So I see that the mask is. Oh, that's to calculate the mask. The mask would be 128. So 25 in that scenario for 1, 255, 255, 128. That 0 would be the mask. So then you need to calculate how many hosts each subnet must support. So the network address range is in /16 range. And using 4 bits for subnetting would be 20 bits. So 32, which is the total amount, minus 20. So let's do this. So 32 total bits minus 20 subnet bits equals 12 bits for hosts in each subnet. So the number of hosts, that makes sense. So 32 total bits minus 20 subnet bits equals 12. Because you had the 16 for the first octet, second octet, and third octet you're just doing 4, so it's going to be a total of 20. So the leftover is going to be 12 bits for hosts. But then it says also in each subnet. Yes, because once you change subnet, you get those back. Yeah. Okay. And then, so you could also think of it as number of hosts per subnet equals 2 to the n minus 2, which n is the number of bits allocated. So 2 to the 4 minus 2. 2 to the 4 is 16 minus 2 is 14. That maybe I just did a typo? Oh, is the number of bits you have allocated for the host ID. Not the leftover, not the bit. Okay. So number of bits left over is what? Allocated for the host ID is... Huh? It's 12. How does that make any sense? Oh, okay. Yeah, so 2 to the 12 minus 2. Let me put that in here. I don't even want to say it like this. I just want to say 2 to the 12 minus 2 equals... What? Oh, I gotta do, how do I do this? Do I do something like that? I do. Nice. So 2 to the 12 is 496, yeah. 4096 minus 2 is 494. Okay, interesting. The way they teach this is quite poor. They can teach it. There's probably a way that you can teach this very straightforwardly. It's not that complicated. It's just the way the information is presented to you makes it complicated. Because it's not like it's not presented in a really clear, logical manner. It's kind of just throwing a whole bunch of weird stuff back and forth. Okay. More bits equals more subnets, less bits equals more hosts. So now you calculate the subnets. Deduct the least significant octet in the mask, 240 in this example, from 256. Gives the next subnet ID of 16. Yeah, so 16, okay. Subsequent IDs are all the lowest subnet ID higher than the one before. So that should equal, how many subnets? 16. Wait, what? So what if I do, so 0 is the first one, plus 16, plus 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So not 0, not counting 0. Or not counting 256. But it'll end at 256. It'll end at 255. So 0. So 0. It starts at 0. Or that's reserved for the whole network address. is .0. But then the first one would be 30.0.1. Or not. Subsequent subnet IDs are the lowest subnet ID higher than the one before. So 32, 48, 64, yeah. Calculate host ranges for each subnet. So the first one's gonna be 16. So what do you do with? You can't use 0 because you allocated 4 already, so you have to start at 16. Those are just lost, so you subtract from the amount. Okay, I see. You lose some of that space. You can't use the full thing because you allocated 4, so you have to start at 16. Yeah, this is very abstractingly interesting to think about. It's the abstractions and the little things you gotta understand about it. But that makes sense. So the first one would be 16. Last one would be 240. Last one would be 240. How is it 30? Why is it 31? I mean, it's not 240 because it says it's not, so it's not, but what? Okay, so why is it 31? The subsequent subnet IDs so calculate host ranges for each subnet. Take subnet address. So hold on, so if it says calculate the subnets, it's gonna be 16, so the next subnet ID is gonna be 172.30.16.0/20, which makes sense. And then subsequent subnets would be 32, 48, 64, which makes sense. Oh, I see. It's 31 because it's just it's within that subnet range. So the first host in the range yeah, so let me write that here. So for first subnet range, let me add that. So the first subnet range would be from 16 to 31 because then at 32 is the next subnet. Okay, it's good enough for now to kind of be okay with what I have, just accept what I have there for it to make sense. What? Why is this being weird? Why did it not pick that up?
basketball game. Exercise for half an hour. Do something that
Trying to not do that. Trying to get this off. Okay. Actually, I forgot I had to do this for my dad real quick. What the hell is this? Anyway, is this a good one?
Game, and much more. Computers use a combination of hardware and software. Hardware is any physical part of the computer, which includes the internal components and the external parts like the monitor and keyboard. Software is any set of instructions that tells the hardware what to do, such as a web browser, media player, or word processor. When most people say computer, they're talking about a personal computer. This can be a desktop computer or a laptop, which has basically the same capabilities, but in a more portable package. Personal computers come in a few different styles. The most common type uses the Windows operating system. Macs or Macintosh computers feature the Mac OS operating system, while Chromebooks run on Chrome OS. Smartphones and other mobile devices mostly use the iOS or Android operating systems. We'll talk more about operating systems in a later video. Computers come in many other shapes and sizes. TVs, game consoles, and even appliances like refrigerators can have built-in computers, although they may not do everything a desktop or a laptop can. There's another type of computer that plays servers. A server sends information to other computers on a network. In fact, every time you use the internet, web servers deliver the web pages that you want to see to your computer.
This probably could be a good one. I gotta share this. And then I gotta want to get one for Windows operating system. How do I do this here? Now let me find one that's like Windows operating system. Intro to Well, let's see what else, because that gave me like no results. Just that one. What else? Okay, let's do intro to Windows. This is only giving me like results for me. I'm trying to not have that, bro. You see, this YouTube is so ass. YouTube is so garbage. It's unusable. It's unusable to search anything. It's unusable. How to use Windows? Not one video. This maybe.
The Windows 10 operating system has been out for more than a couple years now. I still get questions on how to perform certain tasks and which settings to use within the... This video is intended for breaking down those later. Let's first look at the primary window. You'll have your wallpaper in the background. I run a multiple monitor setup, so I typically don't keep shortcuts or anything else on my primary screen. I'll drag some over right now from another monitor. Most software that you install will put a shortcut on your desktop.
This one's not gonna be good.
Unfortunately, Microsoft Windows doesn't come with an
Terrible camera quality.
owner's manual anymore. So today I'm going to help you out with that and show you all the things.
How to use Windows, maybe? Windows 10. This one.
Or totally new to Windows in general, then this video is for you. Let's begin by looking at the overall look and feel of Windows 10. So this whole area here above this bottom bar is called the desktop. On the desktop you have various icons, each of which can be opened to perform some action, usually opening some kind of software. Sometimes it will be to open a website, right? Depending on the kind of shortcut that it is. Now at the bottom here we have all important start button in the lower left hand corner, which gets you into a whole area of controlling and
I wonder if
opening
there's a
software.
LinkedIn Learning thing. No, that's for real. That's what I'm talking about. There's got to be a LinkedIn Learning. Where's LinkedIn? How come I don't got a LinkedIn here? Why isn't it there? Well, now I'm getting a little bit distracted, but I'm trying to see what's going on. I never use LinkedIn, so I'm trying to see what the updates are from people that I might know. Okay, that was about it. How come I can't read? This looks like someone who's trying to be like an ad person. Well, I'm not interested in that, sorry. I don't know you. How do I get to, oh, learning. It's right there. Let's see if this works now, because this always did not work, and I thought I fixed it, but then it would just still not work. Why is this not working still? Okay, there we go. It's gonna work? No, it's not gonna work. Nice. It's gonna, okay. It's just straight up broken, huh? It's impossible to use this thing, huh? Doesn't exist. Oh wait, that doesn't exist. Why is it, why was that even there? This one. And now that we're, why is it like that? Why is it like that? How do I disassociate from this? And now I can switch to this one? Yeah, now I can switch to that one. Okay. Whatever. Okay, there's got to be something here. Microsoft 10. Nothing? That is insane. Seriously, bro? They don't have like... just Microsoft? Oops. No results for Microsoft. What is this? What kind of search is this? Okay, let me switch to this. Maybe this will work. All results. There's no all results? It's crazy, bro. This AI search is terrible. Why even use it? Why? It's literally worse than just normal search. Just the array results. Everything in your database that is matching my string, and that's it. You don't need to even put AI in there. There's no need for it. Technology, maybe it's in technology. Electronics foundations. A lot of introductory stuff here. Look, electronics foundations, IT architecture, 5G. There's gotta be just like operating systems, maybe. Let's try IT help desk. That's like the closest, maybe. macOS Sequoia Essential Training. Windows 10 for IT. Windows 10. I want Windows 10. Like, I want this Mac one, but for just... Oh, Windows 11 Essential Training? Maybe there's going to be Windows 10 Essential Training. Oh, maybe this will be good.
Windows 10 is an operating system. It's the core software on most PC computers. It's the foundation that supports the interface and file storage and the platform for launching and using applications. In a way, you can think of it as the personality of your computer or the language you use to interact with it. My LinkedIn Learning course on Windows 10 will take the big topic of learning Windows 10 and break it into lots of smaller topics to help you get familiar with
software, etc.
Windows 10 for beginners, maybe.
Welcome to Windows 10 Computer Basics. My name's Rick Kamara with Learnit. In this next series of videos, we're going to show you around Windows 10. Now this training is interactive, so after a lesson I'll have you pause the video, practice what you've learned, and then rejoin the video for more learning. If you're enjoying these videos, please like and subscribe. If you want to, when you first boot up your computer,
I still think this one is going to be the
with
best.
the ins and outs of the most popular PC operating system.
Okay, let me see if he's got it.
There's another type of computer. computer that plays an important role in our lives: servers. A server sends information to other computers on a network. In fact, every time you use the internet, web servers deliver the web pages that you want to see to your computer. Servers are also used in many offices to store and share files.
That should be good. This one would be the best, though.
And log into your Microsoft. So, now the multiple ways to work, and looking at into search again, you can see I've got.
They really don't have any good videos for beginners on here.
In this tutorial, I'm going to show you based on each letter. It shows you, it's a tiles menu, which you can resize it, and there are 4 different sizes available. You can launch it, and it shows up here, and this is Excel that showed up.
Excel is the key to unlocking limitless opportunities.
Okay, it's not.
This is Excel for Beginners, the complete course. It doesn't matter how little experience you have in Excel. I promise you that as you watch this video and follow along, that you will learn everything you need to know to get started using Excel effectively. Don't be intimidated by Excel, you can do it. And regardless of what version of Excel you're using, this video is what you need to get started using Excel. In this first section, we're going to look at how to create workbooks in Excel and how to save them, and also we'll learn the basics of what I call the anatomy of a spreadsheet and also the layout in Microsoft Excel. Let's get started. So whenever you start up Excel, it should take you first to a screen similar to this one. You may see a list of recently used spreadsheets, but you'll also have a way to create a new blank workbook. And I'm going to click here just to show that there will often also be templates that you can click to open up and use. You can also search, and there's a button here to more templates. But I'm just going to click blank workbook to open up a brand new, completely blank workbook in Microsoft Excel. And before we create anything in this workbook, let's talk about the anatomy of a spreadsheet. When you're working in Microsoft Excel, you will always have at least one sheet. You can see here in the lower left it says sheet 1, but it's possible to have multiple sheets, and all of those sheets collectively together are called a workbook. Right now my workbook just has the one spreadsheet. In Excel, spreadsheets are made up of columns. You can see this is column E, this is column C, this is column K. And when I select the letter for that column, the entire column gets selected. We also have rows in Excel. This is row 3, this is row 9, this is row 10. So every column has a column letter and every row has a row number. Now the intersection of a column and a row is what we call a cell. So for example, this cell here is the intersection of column E and row 10. And an Excel workbook can contain over 17 billion cells. When you click on a cell, that becomes the active cell. Now, one of the most powerful things about the cells in Excel is that each one can be described by the intersection of its column and row. So for example, this is cell F8, and that's how you say it, F8. What cell is this? This is cell L4, and this is cell B7. Now, because of this fact that you can describe every...
Does he have more stuff? Because this is pretty good. technology for teachers and students. He's got, those are 2 courses. Wow, what are courses to? Does he have just like a plain Windows? He's got Apple. But no Windows. Oh, Microsoft, no. OneDrive, Microsoft Word. Maybe not.
Single cell in Microsoft Excel. There's a lot of exciting possibilities that come about because of that, and you'll see that as you begin using Excel more. The next part of the anatomy of a spreadsheet.
I'll share that later. This would be good, bro, if only.
If you are a novice computer user, this course can get you started with Windows. And if you've used Windows in the past, this course can help you get caught up with the newest version. I'm Nick Brazzi, and I invite you to join me in my course as we take a comprehensive tour of the core functions in Windows 10. You don't really need any specific exercise files to work through this course. Microsoft publishes a significant update to Windows 10 twice a year, and those updates sometimes make changes to how features and tools work. This course was recorded to show the most up-to-date version of Windows, so if you run all of your recommended software updates and you're separate from the different versions of Windows 10, there are also a few different editions, different configurations of Windows for different types of users which sell at different prices. To find out which edition you have, you'll need to go to Settings. To do that, we'll click on the Start button in the bottom left corner, which opens the Start menu. Then we can click on this Gear button. If you are setting up your Windows computer for the very first time, you should decide what type of user account you will use. You will need some account, a username and a password, which you will use each time you sign into your computer. So first, what is this user account all about? Well, on one hand, it's the secure...
Maybe not fully necessary, but... Nothing results. Nothing. Is Mike Chappell a Notre Dame guy? Yeah.
Exam. The Systems Security Certified Practitioner credential is a popular entry-level certification for cybersecurity professionals. The International Information Systems Security Certification Consortium sponsors the SSCP. Now, that name is a mouthful, so most people simply refer to them by their acronym, ISC2. As you work your way through this course, you'll pick up all of the knowledge that you need to earn your SSCP certification. I've been an information security professional for over 25 years in the government, private industry, and higher education. I hold many security certifications, and I've been active as a security certification expert for decades. As we get started, I'll provide you with the background knowledge that you need to begin your preparations for the SSCP exam. We'll cover the value of the SSCP certification, describe the 7 domains of the curriculum, give you an insider's view of the exam, and help you design your own study strategy. Then we'll dive straight into the content. All right, let's get rolling. The SSCP exam is a multiple-choice, computer-based test that you'll take at a Pearson VUE testing center. It's available in English, Japanese, and Spanish. When test day arrives, you'll have a total of 4 hours to take an exam containing 150 questions that cover 7 domains of information security. These include security concepts and practices, access controls, risk identification, monitoring, and analysis, incident response and recovery, cryptography,
that should be one thing, actually, to be honest, right? It's all connected. I like how it just automatically merged it. That's nice. Oh, no, here it is. It just deleted it. Or it just, anyway, yeah, it is. So router, ISP. So exterior looks like this. Interior looks like this. I don't know if I get it, to be honest. Actually, I don't get it. Because either you do or you don't. You know what I'm saying? But I've wasted so much time just trying to like sit and look and stare at... yeah, variable length, bro. I'm just gonna keep going, bro. I'm just gonna keep going. Forget about it, bro. We're almost done with this section, bro. This section was the worst, bro. The worst. patent claims on this one too? Seriously? So I can't use this one? What about yesterday's? Let's see, hold on. Is there radio? Where's radio? Guess I have to do it on YouTube, no? So otherwise, I don't know. Let's see yesterday's video. What is this? SD? What does that mean? Oh, edit processing? Oh, okay. Okay, looks like I can't use this. Okay, whatever. Fine, I won't use it. I won't use it. Fine. Can't use nothing these days, bro. Blocked everything. Blocked, 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 blocked. Can I do the lo-fi girl thing? Radio. What is this link? Oh, radios? Links. Spotify. Napster. That's still a thing? Can't even. You have to log. Okay. Oh, just the page. It's not even. I'm just trying to figure out how to. Maybe there isn't a way. What do they got? They got this. That's what I want, I think. Okay, fine. I can't use Spotify then, whatever. Why doesn't it work? Bruh. Oh wait, I need to do this. Yeah. Yeah, we got that, baby. We got that. Although you can't really see it. Or is that in here? Maybe I could change the color in here. Markdown elements. Tables. Enable table styling. I don't know what that is. Ooh. Custom border with. Oh, there's no color? Can't change the color? It's not center line, so all tables are center. Except for these. I don't know why those aren't. This one somehow is. How do I change it though? I don't know what this is. Table styling. You can't change the color of it. That's tough. Change the border width. Whatever. Oops, this should be. I wish you could change the indentation, numbering indentation. Rendering. That doesn't work. Did I finish coffee? Kind of. Jeez, bro. I honestly have no idea what is going on with this. Jeez, bro. Bro, I don't think I understood anything that this thing is saying. So okay, I don't know why that's not. Okay, we got a space here. This needs a space. Here. Like that. Here we need a space as well. And here we need a space. This one could use a space, to be honest. And this one, why doesn't it have, where is it? Ah, okay, now I do. Thought I did a space there. I guess not. Okay, that's better. You can do a space here. Do I even begin to try to understand this, bro? Okay, company with 3 sites. With different network sizes and IP address requirements. Router A, router B, router C. Router A needs AD30 and 8. Router B just needs 12. And router C just needs 12. Okay. So each have different network sizes and IP address requirements. Except for B. It's the same as C, though. Have subnets representing point-to-point WAN link between the routers. So, variable length subnet mask design process proceeds by identifying the subnets with the most hosts, organizing the scheme in descending order. So remember that that each power of 2 is double than the previous one. Okay, so remember this. Oh, actually, this should be. Let's do these. Oops. There you go. Okay, cheerio. That works a little bit better. What if I change this to info? It's not that much more readable. Okay, so we've established the basic facts there. So now actually doing it. Largest requirement is for 80 hosts, which is this. So 2 to the 6 equals 64 max values, which is not enough. So the next nearest is 2 to the 7. Needs 7 bits for host addressing. Allows for 126 host addresses. 2 to the 7th minus 2. So we come away with the prefix of 32 minus 7 equals 25. The next requirement is met by a 5-bit host address space. Huh? Thank you. Yo, quit yawning, bro. Next requirement is met by a 5-bit host address space. How? That's what I'm trying to figure out. Allows for exactly 30 addresses, but no room for growth. Oh, the next one, okay, 30. I was like, where are you getting? Okay, 7. So the first one was 7, the next one's 5. But then there's no room for growth, so it's exactly 30. So 6 would be safer, but we'll use the closest match instead, so /27. So that comes away from 32 minus 5. /27, okay. Next 3 requirements are for 8, 12, and 12 hosts. Right, okay. All require 4 bits. 2 to the 4 is 16, minus 2 is 18, or minus 2 is 14. What am I saying? Routers use point-to-point links. No more than 2 addresses will be required. Can be met by selecting a /30. Okay, where? How is that happening? All require 4 bits. Or the router itself is a... Oh, the router itself is going to be just... I mean point-to-point links. Oh, here? Well, there's this and this, so it's 3. Routers use point-to-point links. Bink. Bink. Oh, I see. What about this one? There's 3. That's what I'm not understanding, bruh. So main office 1 is router A, requires 80 IP addresses. Mask bits is 7, actual number IP address is 126, prefix 25. Then main office 2, which is router A, is this one? 30, 5, 30, 27. And then main office 3, which is also router A, 8, 4, 14, 28. B is point to point link, so you just need 2. Then A to C is 2, and then B to C. So this, and this, okay. All subnets except for main office 2 have room for growth. Analyzing the final design. We find there are 36 addresses at the end of the range. So would have been spaced to use a /26 prefix for the group of 30 hosts. Actual IP addresses IP address ranges generated by the VLSM design are shown. We don't even need that, just say IP address ranges generated by the VLSM design. Yeah, that's all we need, really. Twenty-five, 27, 28, 28, 28. See, I'm spending a whole entire session just like on this one page, bro. It's not good. some crazy whack, bro. You know what I'm saying? Gather information on account 2. Using IP config command, okay? Answer questions. Are they on the same network? Here's a router. Oh, they don't make the connections there. So I gotta look at the subnet mask and see what that translates to. So what is that 224? How many bits is that? One would be 128. 6 plus 64. 128 plus 64 is 192 plus, what is it? 32? It's 224. Okay. So 1, 2, 3 bits. It's 3 bits for the network mask, which is 2 to the 3. So 2 times 2 is 4 times 2 is 8. So 8 is 32 minus 8 is 24. So slash 24. What? No, 1, 2, 1, 2, 3. 3 bits, so 2 to 3. Oh, it's 8, and then minus 2 is 6. So then, and then 32 minus 6. Is that how that worked? Which one do you do first? No, you take the 7 bits. So 32 minus 8. No, 3 bits. 2 to the 7. So 32 minus 3 is 29. So it's slash 29. So this is slash 29. Okay. Which is the CADR notation for the subnet? It's at slash 29. Are they on the same network? I'm gonna guess no, but how do I figure that out? So slash 29. Based on the subnet mask, how many host IP addresses are created for each network? 2 to the third minus 2. 2 to the third minus 2. 6. Uh-oh. That ain't right. Something not right with that. It's 3 bits. Is 8. Minus 2 is 6. So none of those are correct, so something's wrong. (32 minus 3 is 29. Three. Yeah, 3 bits. Based on the subnet mask, how many host addresses are created for each address? 6. 2 to the 3 minus 2. Doesn't make sense, bro. Something's wrong. I did this wrong and I don't know how. Answer question 7. Okay, well, I have got that all wrong somehow. The link was created between switch 1 and switch 2. Will that allow connectivity between devices? Switch 1 and switch 2. Dude, I don't know how to do this at all. Try the following for marketing 2. Ping the IP address for sales 2. Uh-oh. Oh wait, it's in the question. Okay, let me just ping what sales 2. This one. Okay. Where is it? 192.168.1.12. Oh, 100%. Okay, so there's no connection there. Answer question 10. I don't know why. Probably on different subnets. It's the only thing I can come up with. Different networks. Can probably configure subnet mask. Different networks. I don't know, dude. From sales 1, ping the IP address for sales 2 and marketing 2. Sales 1. Ping sales 2. Could not find. Oh, what? Why didn't that go in right? Okay, timed out still. Okay. And marketing too. Where's marketing too? That one worked. What the? ipconfig? Oh, the IPv4 address is that, which is close to marketing too. Answer question 11. Couldn't say that. That one. Remove the connections between switch 1 and switch 2. Okay. Connect router 1 to the switches as follows. Interface 0. interface 1, switch 2, interface 2 to switch 3. Okay. Test connectivity from account 2. Ping sales 2. What's sales 2? 92.168.1.12. Okay, it worked. Ping IP address for marketing 2. Marketing 2.1.42. Okay, that worked. Answer question 12. What ping commands were successful? Both. Score. 86%. I'll actually take that, baby. Wait, no, it has to be 100 though. How is it that? Okay, that's what I don't understand. I knew I got those two wrong. Okay. So let me read the instruction, bro, because I've got no idea. It doesn't say how to do it. Why is it that though? Oh, it just closed. Okay. Oh, I can look at this though. How is it 27? I don't understand that, bro. I don't understand that at all. It's 3 bits. 1, 2, 3. I don't know how to do this, bro. I literally don't know how to do this. I don't know what is going on here. Am I going from the wrong end? Because it would be 1. dude. I've got no idea how to do that. We just gotta stick with, subnet. Bro, because I've got no idea how to do this. Three months ago, this is new. Let's see.
Ever wondered how large networks are divided into smaller and more manageable pieces? Or how IT professionals ensure efficient use of IP addresses in massive organizations? You're in the right place. Welcome to Whiteboard Doodles, the channel where we simplify tech-related concepts using whiteboard animations. Today, we'll break down the concept of subnetting, showing you how networks are split into subnets to optimize performance and security. Let's dive in. First, let's take a look at what subnetting is. Subnetting is the process of dividing a larger network into smaller, more manageable subnetworks or subnets. By breaking down a network, subnetting helps organize and efficiently allocate IP addresses, preventing waste of IP resources. It enhances network performance by reducing traffic congestion and improves security by isolating different parts of a network. Subnetting also allows network administrators to better manage and control access within different areas of a network, making it easier to troubleshoot and maintain. Each subnet operates independently, yet remains part of the larger network, ensuring and subnet masks. An IP address is a unique numerical label assigned to each device connected to a network, allowing it to communicate with other devices.
That's not the move.
Hello, and this is Sunny. Welcome back. Today my topic is subnetting. A subnet is a log ID and 256.
Nope. This guy.
There's a lot of videos out there that show you how to perform IP subnetting, but it usually involves some type of math. You have to understand the powers of 2. You need to understand how to convert from decimal to binary and back to decimal again. And one of the challenges that you're going to have when you sit down for a certification exam is you may not have the time needed to be able to perform all of those mathematical calculations. You also have to keep in mind that you're sitting down for an exam, and that process can be rather stressful. It's difficult to be able to calculate these things on the fly as the clock is ticking. So I wanted to put together this video that showed the process that I use during a certification exam to be able to subnet very, very quickly without having to go through all of those mathematical processes. Well, there's a little bit of math involved. You do have to be able to use some simple addition to create some tables prior to sitting down and starting the exam. And when you perform the actual subnetting, you have to be able to subtract 1 and add 1. And during an exam, I don't think that kind of math is something we need to worry too much about. This is really a combination of a lot of different processes. I wanted to create a series of subnetting processes that got rid of the math and tried to make the process as simple as possible, removing all opportunities for you to make a mistake during an exam. Now, if you're already familiar with subnetting, some of these processes may be oversimplified, and that's fine. You can skip over the things that you already know. But if you're like me and that stressful test situation is one where it's very difficult to concentrate, then this 7-second subnetting process is going to be for you. Here's a common subnetting problem you might be faced with on an exam. You're given a network configuration. In this case, we have 4 separate networks. You're given an IP address assignment, 192.168.1.0, with a /24 subnet mask. It says that we need an IP addressing scheme with more than one network address that can support 40 devices per subnet. So we've been given the single network address. We need to subnet it out into at least 4 networks, and those 4 networks need to at least have 40 devices per subnet that can be supported with that IP addressing scheme. If we wanted to write this out in a longer form, we could of course write down all of the different subnet mask options. We could convert those to binary so we can use those for calculations later. We might want to reference that back to the CIDR block notation, and we'd be able to see how many networks and how many hosts per network would be for each individual subnet mask. Obviously, on an exam, you don't have this kind of time to write out one of these extensive charts to be able to start calculating a subnet configuration. To do this a little bit faster, we might want to use the power of 2s. We can, of course, create a power of 2 chart or memorize these powers of 2. And then we would look at our subnet mask. We know it was a /24, so we have 24 bits that are already masked. So we might want to borrow some bits from the ones that are left over. We might want to borrow 2 bits for a subnet mask and then use 6 host bits to use on top of that. Now, we know that with those 2 bits that we're borrowing, those subnet bits we would calculate as 2 to the 2nd power, since we're borrowing 2 bits there, and that would give us a value of 4. So the total number of subnets would be 4. We've got 6 host bits, so it would be 2 to the 6th power, and calculating that out would be a 64. And of course, we subtract 2 from that to subtract the broadcast address and the network address, and that leaves us with 62 as the number of hosts per sub.
Is my example, what's up with my example then? What did I do? Yeah, this is the one, okay. Where is it? Here. Not enough, so nearest next match is 2 to the 7. Need 7 bits for host address. Huh? So what was I doing? Hold on, I gotta do this again. Where is it? Here. What was I doing? Oh, I took the host, the network subnet mask bits instead of the host bits, and you have to take the host bits to find the prefix.
Subnet, and there's the answer we were looking for. We now have 4 subnets, and we have 62 possible hosts per subnet, all because we were able to remember that powers of 2. But of course, even this process requires that you do a little bit of work. You need to convert things to binary. You need to figure out how many bits you're going to borrow. You need to calculate this based on the powers of 2, and you either have to have a table already prepared, or you need to remember those powers of 2 so that you can use them very, very quickly on an exam.
Yep.
Remember that when you're subnetting, you're really looking for 4 different addresses. The first one is going to be your network address. Some people call this the subnet address, and it's the very first address that is in a particular subnet. We also want to find the broadcast address. That is the last address in the subnet, and it's the one that is used when a broadcast is sent on an IP version 4 network. We also need to know the first available host address on the network. This will be the one that our workstations and devices will use on that network. And obviously, we then need to know what the last available host address will be for that network so that we can determine the exact range to use for all of our devices. Well, if we take our previous example, you can then see that we would have to write out all of these in binary. We would have to determine the different subnets by changing the binary from 00 to 01 to 10 and then 11, and then calculate all of the first host and last host addresses by comparing the differences in the binary settings for all of these different addresses. Obviously, on an exam, you don't have time to go through this entire process to create all of this information. That's why I created the 7-second subnetting process so that we could very quickly determine all of these in just a matter of seconds and then continue on with what we needed to do for the exam.
No way.
If you've looked at other subnetting videos or you've performed some subnetting yourself, you'll notice there are certain patterns in the math. For example, a 255.255.255.0 subnet mask is a single subnet and it's arranged between 0 and 255. If we grab one extra bit off the end and make it 255.255.255.128, it effectively cuts that in half. So we have a range between 0 and 127 and another range between 128 and 255. If we borrow another bit and make it a .192 at the end, you'll notice we cut it up again into smaller pieces. We're separating these in half every single time. So now we have a process that we can easily see is occurring every single time, and we are going to be able to take advantage of this very common theme whenever we're trying to subnet. We're going to create some tables, and from those tables, we'll be able to calculate exactly what the subnet might be without having to go through any of the binary math. We're going to make 2 charts to help with this subnetting process. The first chart is going to be one that will help us convert from a CIDR block notation to a dotted decimal notation. This is especially helpful when you're given one of these questions that will require you to convert, and having this chart available will allow you to do that very quickly. The way I like to lay this out is to make 4 separate columns, and each one is associated with one of the octets of the IP version 4 IP address. I put a /1 through /8 in the first column, /9 through /16 in the second, /17 through /24, and /25 through /32 in the fourth column. Then I want to calculate how many networks will be available in each one of these, and I put a 2 on the first row, and then I multiply that by 2 each time. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, until I get to the bottom, and the last number should be 256. Then I create an addresses column, and I usually start at the bottom with the number 1, and again I'm doubling each time. I double to 2, 2 times 2 is 4, 4 times 2 is 8, until I get to 128 addresses. And now the final column, which is going to help me make that conversion between the CIDR block notation and the decimal notation. I'll start with 128 at the top, and then I'll add in 64. So I'm effectively adding as I go down the addresses column. 128 plus 64 is 192. 192 plus 32 is 224. 224 plus 16 is 240, until you get to the bottom with 255. The second chart I create is one that shows me the address groupings given a particular subnet mask. If the subnet mask has 128 as that subnet mask, then I know that the subnet will be split into 2. There will be a starting number of 0 and a starting number of 128. If it's a 64 as the number of hosts in a subnet, then I know that my subnet boundaries will be 0, 64, 128, and 192. And I write all of these out. It's obviously pretty easy to memorize an address boundary at 128 addresses or 64 addresses or 32. But when you get into these smaller numbers, especially as it gets higher up in the list, it becomes a lot more difficult to remember where the exact boundary is. And remember, we're trying to do this as quickly as possible. We don't have time to calculate all of these on the fly, so I write everything out during this period so that it's now sitting right in front of me, and I can perform any type of subnetting now in 7 seconds. Of course, all of these charts are the ones that work for me. You may find a different layout or a different way of performing this might work a little bit better. The key for me is to get everything on the page. That way I don't have to perform any of these calculations during the exam itself. Now that we have our charts available, we're able to subnet. The things that we're going to be able to derive from these 2 charts is that we're going to be able to convert the IP address and a CIDR block notation into the decimal form. That first chart that we created allows us to do this very quickly. That chart is also going to show us how many devices per subnet will be on this particular network. The second step of the subnetting phase is to calculate the network address. Some people call this the subnet address. And that second chart that we created allows us to very quickly find the beginning and the end of that particular subnet. Thirdly, we need to know the broadcast address. This will be the last address, and again, that second chart shows us what that ending boundary is. And lastly, we need to calculate the first usable and the last usable IP address of the subnet. That's very easily done by simply adding 1 to the network address and subtracting 1 from the broadcast address. Let's try doing a few of these and see if we can get the hang of it. The first subnetting that we're going to do is address 165.245.12.88 with a /24 subnet mask. Generally, the subnet masks that end on the 8-bit boundaries, the /8, the /16, and the /24, are generally something that's easy to calculate. But let's go through this process to show you how it would flow, and then we'll try some harder subnet masks after this. The first thing we need to do is convert both the IP address and the subnet mask into a decimal format. The IP address is already in decimal format, but this /24 needs to be converted. If we look at our first chart, we need to find the /24. It's in this third column. That's important for later. And you'll see that it converts to a 255. So let's write these down. We've got our IP address at 165.245.12.88. And my subnet mask has a 255 all the way into the third column. So we're going to use 255s all the way up until we hit that third column. And since we are in that third column, everything after that point will have zeros as the subnet mask. I'll show you in a later example how this changes if the mask is not a 255 or a 0. Now that we have both our address and our mask, we need to calculate the network address. If the mask is 255, you bring down the address value at the top, and if the mask is 0, you simply use a 0 in for the network address. That means that if we bring down the 165, the 245, and the 12, and then bring down a 0 where the mask is 0, our network address 165.245.12.0. Now we need to calculate the broadcast address. For the broadcast address, if the mask is 255, we bring down the address number, exactly the same process as if we were calculating the subnet address. But if the mask is 0, we make that value a 255 instead of a 0. So that means our broadcast address is 165.
Nothing. Absolutely nothing. Look at what I've gotten done. I haven't even finished this one, bro. And almost coming up at 4 hours. That's crazy. Let me see, where's the spacing guide they gave me, bro? Because that's garbage. Subnetting, 54 minutes. Yeah. You know what I'm saying? Like, what? What are these guys smoking? This is supposed to be longer than subnetting? Yeah, right. Yeah, right. Yeah, that timing guide is not right at all.
45, 12.255. Now, the process of determining the first usable IP address and the last usable IP address is simply adding a 1 and subtracting a 1. So the first usable IP is the network address plus 1. So it's 165.245.12 plus 1 to that 0 is a 1. And the last IP is a broadcast address minus 1, which means it's 165.245.12.254. And you can see they're listed there. So for this example, you can see what the network broadcast first IP and last IP addresses would be for this particular IP address and subnet mask. Now let's try a subnetting problem that's a little more difficult. This one falls into the 4th octet. It's the same IP address, 165.245.12.88, but on this network, the same addresses would be for, you can see what the network broadcast...
You know what? No, I'm not doing that. Let me just watch the actual learning thing. Is it courses? What is this courses and playlists at, bro? What is it? What's the difference? Is it like a new feature that they just added? Oh, Network Plus. No, study groups. Security Plus training course. Where's the Network Plus? Study groups, Network Plus training course. Here. Network types, WAN, termination, virtual networks, provider links, copper cabling, binary math, IPv4 addressing, NAT communication. Alright, we'll just start here.
If you're configuring IPv4 on a computer, then you need to configure 3 very important addresses. The first address is an IP address. This is an address that uniquely identifies this device on the network. If you look at your IP address and it's a number like 192.168.1.165, that is the unique address that nobody else on your network has. This is how other devices will address or send information to your computer. The second important configuration setting is the subnet mask.
Oh,
this is
in 4K. He knows what's going on. He like me. He like me for real.
a mask that commonly looks like 255.255.255.0 or some other combination of numbers that makes up the subnet mask. This is a number that is used in conjunction with your IP address so that your device understands what IP subnet it happens to live on. This is important when you're trying to route outside of your local IP subnet and you need to send information to a default gateway. If your computer doesn't know what subnet it's on, then it doesn't know what information should be communicated locally and what information should be sent to your default gateway. So we make sure we configure our subnet mask so that your device knows exactly where this data should be sent. And the third configuration setting that we need to put into our computer is that default gateway address. In this example, the default gateway is 192.168.1.1. this is an IP address that is on the same local subnet as your IP address, because this is where you're going to be sending all of the traffic that needs to go outside of this local subnet. If you're configuring these settings on a computer and you ask someone for the local gateway, they're going to provide you with the default gateway IP address, which is another device that happens to be on your local IP subnet. You will also very commonly configure an additional setting that's not listed here that's for your domain name system server or DNS server. We'll discuss DNS configuration settings in a future video. There are other IP addresses configured on your system that are sometimes used in special circumstances. One of these is the loopback address. This, as the name implies, is an address that references itself. So if you send any traffic to a loopback address, you're really sending that to your local machine. The IPv4 address range for a loopback address is between 127.0.0.1 through 127.255.255.254. Normally, we just use the first IP address associated with that. So if you wanted to ping your local loopback address, you would ping 127.0.0.1. It may seem unusual that you would have a separate address that is referenced to your machine, but this is a great way for your local computer to determine if the IP stack inside of your system is working properly. You can perform that ping, and if you get a response back from your system, then that means that the IP stack is working properly. If you ping that loopback address and you get no response from your local computer, then there must be some problem with the TCP/IP stack inside of your operating system. There's also a block of addresses that have been set aside as reserved addresses. When we get into talking about classes of addresses, these are Class E addresses, and they're in a range from 240.0.0.1 through 254.255.255.254. These reserved addresses should not be configured on a local machine or on anything on your production network, and it would be unusual if you would ever run across a reserved address, because everyone understands that these addresses should not be used. And one special address you might find, especially if you're working with routers or other devices with multiple IP addresses, is a virtual IP address, or a VIP. A virtual IP address is one that is assigned internal to your system, but it's not assigned to a physical network adapter. Instead, it's being assigned to a logical network adapter that only exists inside the software of your system. These virtual IP addresses are commonly seen with virtual machines, and you might also see VIPs used inside of routers so that there is always a static IP address that you can reference for that particular router configuration. Let's break apart this IPv4 address and really see how it's constructed. This is our Internet Protocol version 4 address. Sometimes you might hear this address referred to as an OSI Layer 3 address. The addresses that we've been looking at previously are things that you might recognize. For example, here's an IP address of 192.168.1.131. But if you were to convert that decimal value into binary, you would see that the IP address are 4 separate groups of 8 bits apiece. And you can see 8 bits in the first group, 8 bits in the second, 8 bits in the third, and lastly 8 bits in that fourth group. You might also see this referred to as a byte or an octet. They are all exactly the same thing. If you put 4 of those groups together, then you have 32 bits or 4 bytes, and that is what we use to define an IPv4 address. We know from our binary math video that this combination of ones and zeros could be all zeros or it could be all ones. And if we set all of those bits to 1 and then convert them back to decimal, you'll find that the maximum value in any one of these groups is always going to be 255. If you're just getting into IP addressing, you may realize that there's an entire set of addresses on your computer that you've never had to manually configure. If you look at the configuration of the IP addresses on your computer, you may see that they have been automatically assigned an IP address, a subnet mask, a gateway, a DNS server, an NTP server, and perhaps other settings as well. We're able to automatically assign these IP addresses by using DHCP, or Dynamic Host Configuration Protocol. This is a protocol that takes a system that has not been configured with an IP address, communicates over the network using this protocol, and automatically IP addresses are assigned to a local device. This obviously saves a lot of time for the network administrator because they don't have to go to each device manually to configure IP addresses. Instead, a user simply turns on their computer, it communicates automatically to a DHCP server, and that device receives an IP address without any user intervention. DHCP is a common way of automatically assigning IP addresses on both home networks and networks in the enterprise. But there may be times when a DHCP server is not available, and you may find that your device has been assigned an IP address, but it wasn't assigned that IP address from a DHCP server. In that case, you were probably assigned an automatic private IP address, or an APIPA. This is what we call a link local address because the IP address that's assigned to your computer is not able to communicate outside of your local subnet. That means if you've been assigned an APIPA address, then you're not able to communicate out to the internet. This means that if you've been assigned an APIPA address, you're not able to communicate to the internet because routers are not able to forward those IP addresses. One way to tell if you've been assigned an APIPA address is to simply look at the IP address. And if this IP address is between the range of 169.254.0.1 through 169.254.255.254, then you've been assigned an APIPA address. This range is actually slightly smaller than this because the standard for APIPA takes the first and last 256 addresses and assigns them as reserved. So the actual range of IP addresses that can be assigned to a device is between 169.254.1.0 through 169.254.254.255. If a DHCP server is not available, then this APIPA assignment process begins. Your computer picks a random address in this particular range and then sends an ARP to the network to see if anyone else may be currently using that IP address. If there's no response to the ARP, then that address is free and it's assigned to that computer. If you're ever working with a device and you see that it has been assigned an APIPA address, then you're probably connected to a network that doesn't have a DHCP server, or the DHCP server on that network is no longer functioning. On the internet, it's estimated there are over 20 billion different devices that are communicating, and we are increasing the number of devices all the time. But IPv4 only supports 4.29 billion addresses, and we're certainly well over that particular number. The IP address space for IPv4 is also exhausted. If you wanted to get a new IPv4 address that was public and on the internet, you would not be able to easily obtain one. So how are we able to have all of these devices communicating on the internet without actually having enough IP addresses? We're able to use a technique called Network Address Translation, or NAT. This isn't the only reason we might want to use network address translation, but it is one of the most common reasons that people implement NAT on their local devices. We're able to use network address translation to increase the number of available devices because we set aside some very specific IP address ranges as what we call private IP addresses. This comes from RFC, or Request for Comment, number 1918, and it specifically defines what these private IP address ranges would be. This is a very big chart that includes the range, the number of addresses, the classful description, the subnet mask for the range, and the host ID size. But if you're planning to memorize any part of this, it's this first column that is the most important. These are the private IP addresses that you need to know. The first range is 10.0.0.0 through 10.255.255.255. The second range is 172.16.0.0 through 172.31.255.255. And the last private IP address range is 192.168.0.0 through 192.168.255.255. If the IP address of your device is an IP address that is in any of these ranges, then you are using a private IP address, or what you might hear called an RFC 1918 IP address. Very simply, network address translation is when a device changes an IP address as it's communicating through the network. This is commonly done using a router, and in this particular example, this router is providing that translation functionality. On the left side is our private network, and you can see a private address range of 10.10.20.0/24, which means your router and Vala, the device on the left side, are all communicating using these private IP addresses. But Vala would like to talk to the ProfessorMesser.com web server, and you can see that Professor Messer has a public IP address. We need to find some way to have our private addresses communicate to these public addresses and back again. So we'll use our router to perform that translation. Vala will send an IP packet to the Professor Messer website, which means the source address is Vala's IP, which is 10.10.20.50, and she's sending this message to 104.20.19.63, which matches the public IP address on ProfessorMesser.com. When this packet is sent to a local router, the router recognizes that a private IP address is in use and makes a change to that IP address or translates that IP address to a public IP address that has been previously configured inside of that router. It then sends the rest of that information to the destination IP, and we're able to do that because we changed that source IP to a public IP address. This becomes especially important when we need to send information back to Vala. Obviously, we can't send it to the original 10.10.20.50 private IP address, so the Professor Messer website is simply going to reverse the IP addresses it's received. This means that ProfessorMesser.com will now be the source, and the destination IP will be the translated address that was created by this router. This packet is then sent to Router 1, and Router 1 has a previous configuration inside of it that says if anything is received on 94.1.1.1, then it needs to be translated to the internal IP address used by Vala. That router then makes that network address translation and sends the packet to its final destination on Vala's internal IP address of 10.10.20.50. Well, that process works fine if there is a single IP address on the inside that needs to be translated. But what if you have multiple IP addresses, or even tens, hundreds, or thousands of devices that need to communicate? In that situation, you'll perform a special kind of network address translation called a source network address translation, a NAT overload, or a port address translation. Let's take this same situation of Vala, who needs to communicate to the ProfessorMesser.com server. You can see that the source IP address is 10.10.20.50. That is Vala's IP address. And Vala will be communicating to 104.20.19.63, which is the ProfessorMesser.com server. You can also see that we've added the port numbers that are in place. Vala has chosen a random port number as the source port number, and it's added to the end of this IP address as port number 3233. And Vala is communicating to this web server over port 80, and that port 80 has been added to that destination IP address. When this information is received by the router recognizes that the internal IP address needs to be changed to a public IP address, but it also needs to not only change the IP address, but the port number that's in use as well. It creates a table inside of the router that translates between the private IP address and what's available as a public IP address. And this router has determined that we will use 94.1.1.1 as the public IP and a port number of 1055. It then makes that change to the traffic and sends it on to the Professor Messer web server. As with our previous example, when the Professor Messer web server wants to send this information back to Vala, it will change these IP addresses around. When those addresses are received by the router looks up what address has been received over that port number, translates it back to our internal IP address, and sends that traffic to Vala's workstation. This is a process that occurs millions of times a day across all of the routers that we have connected to the internet. And if you're using a router at home or at your place of business, then it's performing this NAT overload or port address translation to be able to provide this network communication. If you're using a desktop computer, a mobile device, or any other device connected to the network, most of your communication is probably going to be unicast. Unicast means that one device is sending information directly to another device. This is a one-to-one communication between these two devices. This is the type of communication where one device will make a request to a server, and that server might respond to that individual request. So if you're connecting to a web server or you're performing a file transfer, it's probably using a unicast communication. This unicast communication works great when one device needs to communicate to another, but unicast becomes more difficult if this single device needs to communicate to multiple devices simultaneously. For example, if you had a real-time streaming media application that used unicast, you would have to send a single separate stream to every single device on the network because there was no other way to communicate other than this one-to-one unicast communication. Unicast is a very common way to communicate, and it's used extensively with both IP version 4 and IP version 6. There are more efficient ways to send traffic to multiple devices on the network simultaneously. One of these ways is to use a broadcast communication where one device can send one piece of information, and that one piece of information is seen by all of the other devices on the network. This is an important characteristic of broadcast communication, that the source device is sending out a single packet of data, and that single packet is then transmitted and broadcast to all of the other devices on the network. This makes for very efficient communication from the source device because it only needs to send that one packet, and yet everyone on the network is able to see that one packet. Obviously, we're not able to send one packet to the internet and somehow communicate with every other device that might be on the internet. This range of communication used by broadcast is called a broadcast domain, and it's usually limited to your local IP subnet. There are a number of routing protocols that rely on broadcast to be able to send updates to all of the other devices on the network. And if you're using IP version 4, then you have ARP requests that use broadcasts extensively. One of the things we found with broadcasts is that once you have a large number of these broadcasts on the network, it can actually create performance problems for all of the other devices. And in IP version 4, we use these broadcasts extensively. When we created IPv6, we were able to correct this issue by limiting the scope of what's sent to all of the devices, and that's why in IPv6 you'll see multicast used instead of broadcasts. Multicast allows you to send a single frame that would only be seen by devices that are interested in receiving that information, and other devices that aren't involved in that communication are not affected by a multicast. We often see multicast used for multimedia communication, stock ticker updates, or if your routing protocols are able to intelligently update other routers on the network using the multicast protocols. Because of the specialization required to only send traffic to interested parties on the network, this is a technology that doesn't tend to scale once you have larger networks involved. This has to be very carefully engineered so that you're able to send multicast from one part of the network to the other, and it's one of the reasons that we don't commonly see multicast communication occurring across the internet. This is a technology that's commonly seen with both IPv4 and IPv6, but since IPv6 does not have broadcasts available, we see multicast used extensively with IPv6 communication. There's another way to communicate where you would have a source device that needs to communicate to a different type of device, and there's many options available on the network to communicate, but ultimately you only need to talk to one of those. This is Anycast, which allows you to communicate to a single device on the network, but that single device could be one of many options available. Anycast is used in both IPv4 and in IPv6. If you were to look at the configuration of these devices, you would see that they appear to have the same unicast address assigned to them. but they're actually Anycast addresses and will respond to any requests made by a device looking for that particular address. This Anycast technology is used extensively on the internet. You can have devices that will request information via Anycast, and the closest device will respond back. This allows you to distribute these servers geographically, and you'll communicate to the device that's closest to you on the network. This is commonly used with domain name services, or DNS, where there are only 13 devices defined as root DNS servers. In reality, there are thousands of root DNS servers available because we've configured them to respond using Anycast. As you begin the process of learning more about IP subnetting, the process of understanding the subnet masks becomes very important. And when we start talking about IPv4 subnetting, you'll often hear about differences between Class A, Class B, and Class C IP subnets. This is referring to a subnetting architecture that technically we've not used since 1993. When IP was originally created, the subnet masks were automatically determined based on what your IP address was. But today you have much more control over the subnet masks because we use classless subnetting. But for the purposes of understanding today's form of subnetting, we're going to look back at how this classful-based subnetting process works. And although today we have much more control over our subnet masks, and we're not limited to simply a Class A, Class B, or Class C, you may still see these classes referenced in casual conversations. And although it seems that we're going back in time to understand a way that we used to provide subnet masking, these have a very important application in today's subnetting. This is the default starting point for subnet masks, and it's important that we understand where a subnet mask begins and how much we're able to subnet from that point. There are technically 5 different classes for IP subnets. You will commonly see Class A, Class B, and Class C used because those are the classes that we are assigning to different workstations. If you're working at all with IPv4 and multicast, then you'll be using Class D addresses and subnet masking, and Class E is a reserved range, and you will never use these IP addresses on your production network. One way to determine the class of an IP address is to look at the first octet in the entire address. If the IP address starts with a 1 through 127, then it's a Class A address. If the IP address starts with 128 through 191, it's Class B, and numbers 192 through 223 designate that as a Class C address. If you're doing IP multicast, then you'll notice those IP addresses start with 224 through 239, and that reserve range is a range between 240 and 254. What's interesting about all of these different classes is that if you convert that very first number to binary and look at just the first 4 bits of that binary value, you'll find that anything that starts with a 0 is Class A, anything that starts with 10 is Class B, 110 is Class C, 1110 is Class D, and all ones would be Class E. Back when subnet masks were automatically defined based on what this IP address was, it would configure the default subnet mask based on that IP address. So if your IP address started with a number between 1 and 127, your subnet mask was 255.0.0.0. If that first octet of the IP address was between 128 and 191, your subnet mask was 255.255.0.0, and if the IP address started with 192 through 223, the subnet mask was 255.255.255.0. In this chart, those are the 3 most important columns: the class, the leading bits, and the default subnet masks. If we are using those values associated with those classes, you'll see the network bits, the remaining bits, the number of networks, and the hosts per networks are calculated based on those default values. Let's go through a number of IP addresses and see if we can determine what the default class is for that address. We'll start with this IP address of 17.22.90.7. We'll look at the first octet, which is 17, and we know that any number between 1 and 127 is a Class A address. The next on our list is 220.10.77.40. Looking at that 220 at the beginning and referring back to our previous chart, we would call this a Class C address. The next IP address is 165.245.0.1, and again, referring to our chart or looking at a 165, converting it to binary, looking at the first 4 bits, you should be able to determine that that is a Class B address. 128.90.10.2 begins with a 128, which means that it is also a Class B address. For the IP address of 191.77.24.250, we look at that first octet, which is 191, and that 191 falls into the category of a Class B address. And lastly, 192.1.12.5, that 192 is one more than 191, but that is the difference between a Class B and a Class C address. When you're working with IP subnetting, there are 4 separate values that you need to be able to calculate. We're going to go through these 4 here, and then I'll demonstrate how you can perform some practical calculations to determine all 4 of these values. The first value is the network address. This is the first IP address that's in a subnet. To calculate the network address, we set all host bits in the address to 0 or 0 decimal, and we calculate what the decimal value of that might be. The second value you'll need to calculate is the first usable host address. If you know the network address, then you can calculate that easily because it's one number higher than the network address. The next value we need to calculate is the network broadcast address. The broadcast address is the last IP address that's in a subnet. When we calculated the network address, we set all host bits to 0. To calculate the broadcast address, we set all host bits to 1. And then we perform a conversion to decimal to determine what the network broadcast address is. The last value we'll need to calculate is the last usable host address, which is one number lower than the broadcast address. So we take the broadcast address that we just calculated, we subtract 1, and we have the last usable host address. Now that you understand the process, let's perform some practical calculations. We need to calculate the subnet address, the first host address, the broadcast address, and the last usable host address. Let's start with an IP address of 10.74.222.11. This address is a Class A address. We know that because we looked at the first octet. We compared this to the chart that we had earlier, and this address certainly is a Class A address. If we take the default subnet mask for this address, we know that this Class A address is 255.0.0.0. Because we know that the subnet mask is 255.0.0.0, we can add a separation in this particular address where all of the 255 values are on the left and all of the 0 values are on the right. And that puts this divider right after that first octet. So 10 is on one side of the divider and all of the other octets are on the other side of the divider. If we write this out and separate things on the left side of the divider as the network portion of the address and everything on the right is the host portion of the IP address, then you can see the network portion is 10 dot, and then the host portion is 74.222.11. Now we need to start performing some calculations to determine what the subnet address or network address happens to be. So we're going to set all host bits to 0. That means for this IP address, the network address is 10.0.0.0 because we changed all of those host addresses to zeros. We also know that the first usable IP address in this subnet is one address higher than the network address, so we add 1 to this 0.0.0, which gives us 0.0.1, so your entire first host address is 10.0.0.1. To calculate the broadcast address, we change all of the host numbers to all ones. In decimal, this is all 255s. So your broadcast address for this subnet is 10.255.255.255. We also know the last usable IP address on this subnet is one value lower than the broadcast address, which means that our last usable host address is 10.255.255.254. As long as you know the class and you know where to make that dividing line, all of the other calculations should fall right into place as long as you follow those simple rules. Let's look at another IP address. We'll look at 172.16.88.200. The first thing we should do is find out what class this address is associated with. We need to look at that first octet, which is 172, which places this IP address into the Class B category. Knowing that this is a Class B address, we know that the default subnet mask is 255.255.0.0. That puts our network address on the first two octets, and the host part of the address is the last two octets. If we were to write this out in our chart, the network portion of the address is 172.16, and the host part of the address is 88.200. The first thing we need to do is determine what the subnet or network address is. We set all host bits to 0, which means that the network address is 172.16.0.0. To determine the first usable IP address of the subnet, we add 1 to the host side, meaning that we have a first host address of 172.16.0.1. To calculate the broadcast address, we set all of the host bits to 1, which in decimal is 255, meaning that our broadcast address is 172.16.255.255. And the last usable address is one address lower than the broadcast address, meaning that the last usable host address is 172.16.255.254. Here's one more. We'll look at the IP address of 192.168.4.77. Looking at that first octet, we can see that the 192 means that this is a Class C address. That also means that the default subnet mask for Class C is 255.255.255.0. We'll put this IP address separator right after that third octet and put it into our chart. So the network portion of the IP address is 192.168.4, and the host portion of the IP address is 77. Let's perform the same 4 calculations. We'll determine what the network address is by setting all the host bits to 0. In this case, the host bits are only that last octet, so your network address is 192.168.4.0. If we add 1 to that value to determine the first usable host address, we come up with the IP address of 192.168.4.1. Determining the broadcast address means that we set all of the host bits to 1, or 255 in decimal, so your broadcast address is 192.168.4.255, and the last usable IP address of this subnet is 1 fewer than the broadcast address, making that last usable host address 192.168.4.254. By using these rules, you can easily calculate what all of these values are for IP addresses that happen to have subnet masks that correlate to a Class A, Class B, or Class C subnet mask. You may find that the IP addresses on your network use these delineations at each octet point, which makes it a very easy calculation. But these days, we're able to subnet into any of these octets, and in future videos, we'll look at how to perform calculations if you're using classless subnetting. In this video, we're going to go into detail with IPv4 subnet masks. So if you haven't already watched the video on binary math and classful subnetting, make sure you check the video description and go back and look at those videos first. Most of what we'll do in this video focuses on some techniques that you'll learn in those previous 2 videos. A subnet mask is a contiguous series of ones. You'll notice that all of the ones are on the left side of the subnet mask, and the zeros are on the right side of the subnet mask. For example, this is a subnet mask. You can see there are contiguous ones all the way from the left up until this point, and the remainder of the subnet mask is all zeros. You will not have a subnet mask that has interlacing ones and zeros between it. All the ones will always be on the left, and all the zeros will always be on the right. If you were to convert this binary value into decimal values, you'll find that this subnet mask is also 255.255.255.0 in decimal. And you can also use a shortcut to describe this subnet mask by counting up the number of ones and putting that right after the slash value. So this subnet mask would also be referred to as a /24. We refer to this shortcut of using the slash with the number after it as CIDR block notation. That's CIDR. It stands for Classless Interdomain Routing. You might also hear this referred to as CIDR block notation, slash notation, or prefix notation. The subnet mask is used to delineate the network part of the IP address from the host part of the IP address. All of the ones designate the network portion. In this case, there are 24 bits of the network portion of the subnet mask, and there are 8 bits set to 0. That would be the host portion of the subnet mask. Let's do another subnet mask calculation. This time we'll take this subnet mask of all ones in the first 2 octets and all zeros in the last 2 octets. If we were to write all of these out as the number of bits that are set to 1 in each of those octets, we have 8 in the first octet, 8 in the second, 0 in the third, and 0 in the fourth. If you add all of those up, you can summarize this subnet mask as a /16, because we have 8 plus 8 plus 0 plus 0, which equals 16. If you break down this subnet mask into the portion designated with ones and the portion with zeros, you can see that there are 16 bits on the network side and 16 bits set to 0. That would be the host side. Let's do another CIDR block notation calculation, this time with a subnet mask that doesn't follow those 8-bit octets. In this example, we have a subnet mask that has all ones in the first 3 octets, but the last octet has 11000000. But it's the same calculation that we've used for everything else. We count up the number of ones, which is 8 plus 8 plus 8 plus 2, which means that the total number of ones would be 26. That means that the CIDR block notation for the subnet mask is a /26. This means that the network portion of the subnet mask is 26 bits long and the host portion is 6 bits long. Let's do one more of these CIDR block notation calculations. In this subnet mask, we have all ones in the first octet. We have 11110000 in the second octet, and then the third and fourth octet are all zeros. If we count up the number of ones, we have 8 in the first octet and 4 in the second, which means that this subnet mask is also known as a /12. This means that the network portion of the subnet mask is 12 bits in length, which means all of the remaining bits are the host bits. In this case, that would be 20 bits. One of the things that we will commonly do when seeing these binary subnet masks is try to convert them back to decimal. And one easy way to do this is to build a chart of all of the possible combinations. For example, all 8 bits set to 0 would obviously be a decimal value of 0. If that first bit is set to 1, the decimal value is 128. The first 2 bits set to 1 are 192. The first 3 bits set to 1 are 224, and so on. If you refer back to our video on binary math, then you'll be able to easily calculate the decimal value from the binary and vice versa. It may help on your exam if you're able to write out this chart on your whiteboard, either the physical one in a testing center or the digital whiteboard that they give you online, so you have an easy way to reference these values without having to perform manual calculations each time. So let's perform another calculation of the subnet mask, but we're going to use our chart here to perform a quick binary to decimal conversion. Here's our subnet mask. It's 1111 1111 11110000, and then the last 2 octets are all zeros. Again, we would look at these binary versions of the subnet mask and quickly convert them to decimal. All ones is the same thing as a decimal 255, and the conversion of 11110000, if we look at our chart, converts to 240. That means that this subnet mask written in decimal is 255.240.0.0. And if we count the number of ones in this subnet mask, we can see that there are 12 ones, which means that this subnet mask could also be written as a /12. That means that 12 bits in the subnet mask are the network bits, and the last 20 bits are the host bits. Let's do another subnet mask calculation. In this case, we have all ones in the first 2 octets. In the third octet, we have 3 ones and 5 zeros, and the last octet is all zeros. If we look at our binary to decimal conversion chart, we can see that the first 2 octets are 255. The third octet is 3 ones and 5 zeros, and that is 224. You can see we bring the 224 down, and all zeros is obviously 0, which means that this subnet mask is 255.255.224.0. And if we count the number of ones, we can see that this is a /19 subnet mask with 19 bits for the network and 13 bits left for the host. Let's do the same calculation, but let's do it in reverse. Let's start with a /26. One of the first things we can do is to write that out in binary, which means there will be 26 ones. And if we write that out into our 4 octets, our first 3 octets are all ones, the last octet is 1 1, and all of the zeros are remaining. If we perform the conversion from binary to decimal, then this /26 is also known as a 255.255.255.192 subnet mask. That means that there are 26 bits set aside for the network, and the remaining 6 bits are the host bits. And let's do one more of these in reverse with a /20 subnet mask. We'll write out all of those ones in binary form. A /20 means there are 21, so our first 2 octets are all ones. The third octet is 11110000, and the last octet is all zeros. If we perform our conversion from binary to decimal, that means that the /20 subnet mask is 255.255.240.0. Our network bits would be 20 bits, and our host bits are the remaining 12 bits. Being able to perform these calculations quickly will help you during your subnetting questions, so you may want to try taking a number of different / values or binary values and see if you can calculate back what the decimal form and / values might be for all of these subnet masks. In this video, we'll talk about how you would calculate IPv4 subnets and hosts. This video builds on a number of topics covered in previous videos, so make sure you go back and watch the videos on binary math, classful subnetting, and IPv4 subnet masks. If you've ever seen a network diagram, then you've probably seen a mixture of routers and IP addresses with subnet masks, and each one of these networks is subnetted into its own range of IP addresses. Well, the question, of course, is why do we go through this process of performing all of these calculations, splitting the network up into these smaller pieces, and having to manage all of these separate IP subnets? Well, one of the most common reasons is that it's very difficult to connect all devices to all other devices in the world simultaneously. It would require a massive amount of technology to be able to know where every single device happens to be at any particular time. Instead, we use routers to separate the network into smaller pieces, and we simply send our traffic to the next router, who then determines where the next route would be after that. It's a much simpler way of being able to manage such a large number of devices on a network and yet still allow us to communicate to all of these separate endpoints. Prior to 1993, your subnet masks was set automatically based on what your IP address happened to be. This is a class-based subnetting method that we very quickly found was not able to be as flexible as we needed on today's modern networks. Instead, today we use what's called VLSM, or variable length subnet masks, where we, the network administrators, can determine what the best subnet masks might be for our particular network. You can think of this as having an entire pie and slicing the pie into smaller pieces. Or maybe you have a pizza and you're cutting the pizza into smaller pieces from there. You're able to customize depending on the requirements for the number of networks and number of hosts on your network. Variable length subnet masking allows us to use different subnet masks depending on the requirement. So although a network of 10.0.0.0/8 would be a Class A network that has that 255.0.0.0 subnet mask, we may want a network with more flexibility. So variable length subnet mask allows us to set a subnet mask of 10.0.1.0/24 or 10.0.8.0/26. The real question then becomes, what are the size of the slices on the pizza that you're going to cut? In class-based subnetting, we would have a network address of 10.0.0.0, and the subnet mask would be 255.0.0.0. That is a Class A subnet for that particular IP address range. And if you looked at this particular subnet mask in binary form, we would have all ones in the first octet and zeros in the remaining 3 octets. That means that the subnet mask is 255.0.0.0 or a /8. That has 8 bits for the network and 24 bits for the host. But we may want to take this pizza and cut it into smaller pieces. So instead of having our subnet mask separation after that first octet, we're going to move the subnet mask down a bit until we find exactly where we would like it to be. For example, if we place it right after the third octet, we still have our 8 network bits, but now we've created 16 new bits in the middle that are our subnet bits. This leaves us with 8 bits at the end for our host. And if we perform calculations on all of these bits, we can see now that the subnet mask is 255.255.255.0 or a /24. This is the challenge that the network administrator has, is to determine where to draw that line. And it's this determination on number of subnet bits and the number of host bits that you have left over that helps the administrator determine how they should best engineer the subnetting for their network. One of the things we learned in our video on binary math was the powers of 2. For example, 2 to the first power is 2, 2 to the 5th power is 32, and 2 to the 12th power is 4096. We can use these powers of 2 to help calculate the number of subnets and the number of hosts that are available depending on how many bits we might have. The number of subnets can be calculated as 2 to the subnet bits power, and the number of hosts per subnet is 2 to the host bits power minus 2. Let's use these calculations in a practical example on subnetting. Here in the upper left, we have our numbers of subnets calculation and our hosts per subnet calculation, along with our powers of 2 table. Let's take an example of an IP address of 10.1.1.0/24, and let's perform some subnetting. We're going to take that /24 subnet mask and list it out in binary form with 24 ones and 8 zeros at the end. We also know that this IP address is a Class A address because it starts with a 10 in its first octet, so we know that the default is to have 8 network bits. But in this case, we've specified a /24, so the number of bits that we will use will actually be extended another 16 bits, and those will be our subnet bits. The remaining bits are the 8 bits on the end, and those will be our host bits. Now we can perform some calculations. We know that the number of subnets is 2 to the subnet bits power, which means that you have 2 to the 16th power. And if we look at our chart, 2 to the 16th power is 65,536. The next calculation is the host per subnet, which is 2 to the host bits minus 2. We know that we have 8 host bits, so 2 to the 8th power minus 2 is the same thing as 256 minus 2, or 254 hosts per subnet. So for this particular IP address, we know there is a maximum of 65,536 subnets that we can create, and on each one of those subnets, we can put a maximum of 254 hosts. Let's do another one. This IP address is 192.168.11.0/26, and that /26 is the same as putting 26 ones, and then we have 6 zeros left over at the end. This IP address starts with a 192, which means it's a Class C address by default, so we will specify the 24 bits that are required for Class C. But we would like to also use those last 2 bits to make up the 26 bits, so we'll extend that out another 2 bits, and those remaining 2 bits are our subnet bits. That means the last 6 bits are our host bits, And now we can perform that calculation of number of subnets, which is 2 to the subnet bits, or 2 to the second power, or 4 total subnets. And since our host bits are 6, we can specify the number of hosts per subnet as 2 to the 6th power minus 2, which is also 64 minus 2, or the value of 62. That means for this IP address of 192.168.11.0/26, this is one subnet that is a maximum of 4 total, and on all 4 of those subnets, we can have a maximum number of 62 hosts on each subnet. This is the same process every time, and it works with any IP address. Let's take 172.16.55.0/21, and we'll put all 21 of those bits of the subnet mask written out in binary form. We know that the 172 is a Class B address, so the number of network bits would be the first 16 bits of the subnet mask. Then we'll also extend this out, the extra 5 bits that we have, making up the 21 bits of the subnet mask. So our subnet bits are 5, and the remaining bits are the host bits, or 11 total bits. Performing our calculations, we know that the total subnets is 5 bits, or 2 to the 5th power, 32 subnets total. And the total number of hosts that you can have on a subnet is 11 bits. And if you do the calculation, 2 to the 11th power minus 2 equals 2,046 hosts per subnet. You could perform this calculation manually on your exam to determine what the number of subnets and number of hosts might be, but you can see there is a lot of effort that goes into converting this to binary, converting things back to decimal, and then performing these calculations. In the next couple of videos, we'll show you some different shortcut techniques that can help you perform these calculations very quickly on your exam or any other time. In previous videos, we've looked at the process for manually subnetting an IP address. For example, let's take a common question like this one, where we have a network that has given us an IP address assignment of 192.168.1.0/24, but we need an IP addressing scheme with more than one network address and the support of 40 devices per subnet. How can we subnet this network address to give us multiple networks, but still allow for 40 devices per subnet? You could certainly calculate this manually by writing down the CIDR notation, determining what the decimal mask would be associated with that CIDR block notation, and then manually writing out what the binary version of that subnet mask is. You could also calculate the number of networks and the number of hosts per network based on that particular subnet mask, and then you could calculate additional networks by adding on to the CIDR notation and performing the same calculations for each possible scenario. This question asked for 40 devices per subnet, so after creating this chart, we can then look at the host per subnet. We can see that a /27 only supports 30 devices per subnet, but a /26 allows for 4 networks with a total of 62 hosts per network on each of those 4 subnets. We could then perform the same calculations that we did in a previous video where we had that IP address and subnet mask. We then wrote down the binary version of both of those and designated what portion of the subnet mask was the network part of the mask, the subnet bits that we were able to borrow, and then the host bits that were left over at the end. You can see in this example, there were 24 network bits, there are 2 subnet bits, and 6 host bits. Now we can perform those calculations that we did from the previous video to determine the total subnets. We take the 2 to the 2nd power, because we had 2 subnets available. That gives us a value of 4 total subnets. And then we can calculate hosts per subnet, which in this case is 6 bits in length, which would be 2 to the 6th power minus 2, or 64 minus 2, which gives us 62. After performing that entire process, you now have everything you need to be able to answer that question. But part of the challenge with this is that it takes quite a bit of time to perform these conversions. Ultimately, we're looking for 4 very important addresses. We want the network address or subnet ID. This is the first address that is in the subnet. We want the broadcast address, which is the last IP address in the subnet range. We want the first available host address, which is one more than the subnet ID. And then we want the last available host address, which is one fewer than the broadcast address. To be able to calculate this in binary, we would have to write out all of the binary combinations for that network address and subnet mask to be able to determine what all of the different networks are, all of their broadcast addresses, the first host and the last host for each of those individual subnets. And as you can see, just doing a very small number of subnets, 4 separate subnets, can result in a large amount of calculations and conversions between decimal and binary. And on your exam, you don't have time to create these large and extensive charts, so we need some type of shortcut that can make this process much quicker. One popular shortcut that's used for the subnetting process is called the magic number method. This is a relatively straightforward process where you can do most of the math in your head or the minimal amount of math that you would need to be able to calculate this particular subnet. You may find that there are some charts that might help you, and in this video, we'll show you how to perform these calculations in your head, and we'll show you what these calculations would look like if you had a chart available. If you were to write down all of the different CIDR block notations and their correlating decimal subnet mask, you could create an extensive chart with all of that information inside of it. But one of the things you'll notice is that there are some repeating values. For example, a /9 is 255.128.0.0, and if we look down at the /17, we can see that that 128 shows up again. There's a lot of repeating processes involved in calculating these subnet masks, and we can take advantage of this by using that as a shortcut in this magic number method. If you wanted to create a very quick chart that could help you calculate the CIDR block notation to decimal version, then you can write out something like this that uses the /9, /17, and /25 to show you in the interesting octet that the number you would use to convert to decimal is a 128. We can use a chart like this as we go through the magic number method, or really any method that you use to perform any type of subnetting shortcut. If you wanted to create a complete chart for the magic number method, you would add another row for the magic number. Here we've turned this on its side so we can see the CIDR block notation for what we call our interesting octet number 2, number 3, and number 4, and you can see all the slash values associated with those octets. Then for each of those octets, you can see the subnet mask that would be used for that interesting octet. And as you'll find out in a moment, you'll be able to use a magic number value for each of those, and we can calculate that in this row. The magic number method is starting at 128, and then you divide that in 2 for each one of these. So it would be 128, 64, 32, 16, 8, 4, 2, and 1. This chart will give you almost everything you need to perform the magic number method without having to calculate a lot of these details in your head. If you're someone who is able to memorize the CIDR block notations very well, then you could easily have all of these values in the first 3 rows and the last row committed to memory. Then the only thing you would have to remember is the magic number row. Another chart that's useful to have for calculating host ranges is one that separates out all of these different ranges and gives you the starting and ending numbers. For example, in a host range of 128, we have 2 separate blocks of hosts that we could use between 0 and 127, and then 128 to 255. The next block would be a block of 64 addresses, 0, 64, 128, and 192. This might be relatively easy to remember until you get into the smaller blocks. For example, if it's an address range of 8 hosts per subnet, then you'd have to remember 0, 8, 16, 24, 32, 40, 48, 56, 64, and so on. If you're very good at multiplication and division, then you may not need this chart. But if you're someone like me that needs a chart to give you the answer without having to perform the math, you might want to spend a minute or 2 at the beginning of the exam to create this chart. However, with the magic number process, you may find that these charts are unnecessary and you can perform most of the calculations in your head. The steps involved at learning how to subnet with the magic number process are these. We start by converting the subnet mask to decimal. So if you've been giving a CIDR block notation, you need to understand what the decimal notation of that would be. We would then need to identify what we call the interesting octet, and I'll explain more of that in just a moment. We would then calculate our magic number based on the values in that interesting octet, and that's very often a calculation of 256 minus the interesting octet value. You would from there calculate the host range, calculate the network address, and calculate the broadcast address. Let's run through the magic number process now and see how it differs from performing exactly the same subnetting process in binary. The first thing we want to do is to identify the subnet ID. We would need 4 octet columns, and in each one of these rows, we're going to add the subnet mask. We'll determine an action that will perform to that subnet mask. We'll put the IP addresses in that we will be subnetting, and we'll determine what the subnet ID is in this bottom row. Let's start with the IP address of 165.245.77.14, and that device has a subnet mask of 255.255.240.0. So let's add our subnet mask, 255.255.240.0, and let's add our IP address, 165.245.77.14. Our first step in finding the subnet ID is to look at the subnet mask, and if that subnet mask is 255, we want to perform a copy action on the IP address and simply copy the IP address down to the last row. We'll do this with all of the subnet masks that are 255, and in this case, that would be our first 2 octets. Then we want to find any octet of the subnet mask that happens to be 0. We're going to also copy down not the IP address, but we're going to copy that 0. So now we have numbers that are in our first and second octet and another value in the fourth octet. The only one that we haven't touched is our third octet, where the subnet mask happens to be the value of 240. If there is a value that's not 255 and it's not 0, then we are going to identify that octet as our interesting octet. Now that we know our interesting octet and we know what subnet mask happens to be in the interesting octet, we need to perform a calculation. Let's take the number 256, subtract from that the subnet mask value that's in our interesting octet, and in this example, it would be 256 minus 240, which gives us a value of 16. We call this value of 16 our magic number. This magic number is the number of hosts that are on this particular subnet. If we look at the chart that we created earlier for the values of 16, we can see that they range from 0, 16, 32, 48, 64, and so on. We know that the value for our IP address is 77. So if we look in our range for where 77 might sit, it is between 64 and 80. This means that our subnet ID in this particular example is 64, and we can bring that down to show the subnet ID of 165.245.64.0. Now that we know our subnet ID, we need to calculate our broadcast address. And we've changed our chart just a little bit. We have our subnet mask at the top and the action row as second, but our third row is now the subnet ID that we just identified, which is 165.245.64.0. And we're going to try to determine the broadcast address. This process is very similar to what we just did to perform that subnet ID calculation. We're going to look at the subnet mask, and if it's 255, we copy down the subnet ID. So in this case, that first column would be copied down the 165. Since the second column also shows a 255, we will copy that 245 and bring it down into the last row. If our subnet mask happens to have a 0, we'll identify that as a 0 subnet mask. And instead of bringing down the 0, since this is the broadcast address, we're going to bring down the value of 255. This means that we have 3 of the 4 numbers we need. And since one of these numbers in our subnet mask was not a 255 and it was not a 0, then we again have an interesting octet. And of course, we knew that the third octet was the interesting octet based on the previous calculation that we did in the last slide. Now we need to calculate the broadcast address, and this follows exactly the same process we did earlier to find the magic number. We take the value 256, we subtract from that the subnet mask, and in this case we come up with the value of 16. In this case, we're going to calculate a broadcast address, and the way that we calculate that is by using this magic number, by taking the subnet ID, adding to that the magic number, and then subtracting 1 from that value. This means that the value for the broadcast address in that interesting octet would be 64 plus 16, which is 80. You subtract 1, and you get the value of 79. Our broadcast address then is 165.245.79.255. As you can probably tell already, there are a lot of opportunities to be able to perform some shortcuts, and in our next example, we'll take advantage of some of those opportunities. We now know our IP address, our subnet mask, our subnet ID, and our broadcast. Let's find out what the host range would be for this particular network. We don't have to refer back to our chart at all for this. Instead, we'll find the subnet ID and add 1 to it. We know that our subnet ID is 165.245.64.0, which means that the first host would be 165.245.64.1. The last host is the broadcast address -1. So again, we can do this with no additional calculations. We simply take 165.245.79.255, subtract 1, and that gives us the value of 165.245.79.254. Now we have all of the values that we need to be able to perform our calculations. We have our IP address. address, our subnet mask, our we take 165.245.79.255, subtract 1, 65. We know that our subnet ID is one of some of those. Subnet ID, we now know our IP address, our subnet mask, our subnet ID, and our broadcast. Let's find out what the host range would be for this particular network. We don't have to refer back to our chart at all for this. Instead, we'll find the subnet ID and add 1 to it. We know that our subnet ID is 165.245.64.0, which means that the first host would be 165.245.64.1. The last host is the broadcast address -1. So again, we can do this with no additional calculations. We simply take 165.245.79.255, subtract 1, and that gives us the value of 165.245.79.254. Now we have all of the values that we need to be able
I want to go back, hold up to the
to perform
because I had a
-1
pop up in my
to it. We know example 9. Calculate in rows the sub 4.0 4.0 between 64 and 80. This means that our subnet ID in this
subnet ID for this IP. Okay. Now I can go all the way back to
at all for this. Instead, we'll find the subnet ID and add 1 to it. We know that our subnet ID is 165.245.64.0, which means that the first host would be 165.245.64.1. The last host is the broadcast address minus 1. So again, we can do this with no additional calculations. We simply take 165.245.79.255, subtract 1, and that gives us the value of 165.245.79.254. Now we have all of the values that we need to be able to perform our calculations. We have our IP address, our subnet mask, our subnet ID, our broadcast address, the first host, and the last host on that subnet. Let's perform another subnetting example, except this time let's take advantage of a few shortcuts that might be available. We'll use the IP address of 10.180.122.244 and a subnet mask of 255.248.0.0. We'll start by adding our subnet mask into our chart and our IP address into our chart. We'll identify all of the masks that have a 255 and copy down the IP address from there. And we'll look at any subnet mask octets that have a 0. We'll bring down the 0 for each of those columns. Our interesting octet in this case would be the second octet that has the value of 248. We'll perform our magic number calculation by taking 256, subtracting the subnet mask of 248, and determine that our magic number is 8. If we are able to look at our chart of all of those values of 8, or you're able to calculate the multiples of 8 in your head, you can see that the 180 is the IP address we're looking for, so we need to find the starting address for that particular block. 180 is down in this chart under the block that starts with 176, so we'll put the 176 into our chart, which means our subnet ID is 10.176.0.0. We perform a similar process to find the broadcast address, and we've replaced the IP address with the subnet ID row. And of course, we're going to look at any of the subnet masks that have a 255 or a 0. If there's a 255, we bring down the subnet ID, and if there is a 0, we bring down the value of 255. In this particular case, the first column, we bring down the subnet ID of 10, and the third and fourth octet, we bring down the values of 255. And of course, as we saw previously, our interesting octet is the second octet. We perform our magic number calculation again. 256 minus 248 gives us the same magic number of 8. Since we already knew that, we could have possibly skipped this step at this point. And we need to calculate the broadcast address for that second octet by taking our subnet ID, adding the magic number, and subtracting 1. In this case, our subnet ID is 176. We add the value of 8, subtract 1 from that to give us a value of 183. So our broadcast address for this subnet is 10.183.255.255. Calculating the first available host and last available host then is simply adding 1 to the subnet ID and subtracting 1 from the broadcast, which means that our first host is 10.176.0.1 and the last host is 10.183.255.254. If we refer back to the chart that I mentioned earlier in the video, we can speed this process up. 10. First host is to the subnet ID and subtracting 1 from the broadcast, which means that our first host is 10.176.0.1 and the last host is 10.183.255.254. If we refer back to the chart that I mentioned earlier in the video, we can speed this process up a bit. Let's take the IP address of 172.16.242.133/27. Let's first find the /27, and we can see that the subnet mask for that interesting octet is 224. So our subnet mask would be 255.255.255.224 because we know that the interesting octet was octet 4. We can then either calculate the magic number, which would be 256 minus that 224, or we can refer to our chart where we've already written in that the magic number is 32. We know from our chart that a /27 means that our interesting octet is 4 because you're in 254. If we refer back to the chart that I mentioned earlier in the video, we can speed this process up a bit. Let's take the IP address of 172.16.242.133/27. Let's first find the /27, and we can see that the subnet mask for that interesting octet is 224. So our subnet mask would be 255.255.255.224 because we know that the interesting octet was octet 4. We can then either calculate the magic number, which would be 256 minus that 224, or we can refer to our chart where we've already written in the magic number is 32. We know from our chart that a /27 means that our interesting octet is octet 4, and in that octet we have the value of 133. If we go to a chart that shows us those 32 hosts per subnet, we can calculate where that 133 might be, and it starts with a subnet that has a 128. That means that the 128 is the beginning of the subnet, and 1 minus 160 would be the end of that subnet. Let's now summarize all of this subnetting information that we've discovered. We started with this IP address of 172.16.242.133/27. We converted the /27 from that CIDR block notation to decimal, which means that our subnet mask is 255.255.255.224. We also calculated our magic number, and we know that our magic number is 32. We also calculated, based on where our 133 sits in those values of 32 devices per subnet, that the network starts with a 128. So your subnet ID is 172.16.242.128, and the broadcast address is 128 plus 32 minus 1, meaning that your broadcast would be 172.16.242.159.
Wait, what? Every 32. Oh, within that subnet. Yeah. Yep. Okay, never mind. Yeah.
We can then now, based on the subnet ID and the broadcast address, add 1 to the subnet ID to get your first IP address and subtract 1 from the broadcast to get our last IP address. So we now have all of the values we need to understand this particular subnet of 172.16.242.133/27. If you think the magic number method is one that works best for you, then grab some additional IP address ranges and CIDR block notations and run through this process a number of times. You'll find very quickly that you're able to find your own shortcuts, identify where you can speed through this process, and you'll be able to perform these subnetting tasks very quickly on your exam.
All right. I kind of got it. I think so. That helped. Spent like the whole day just doing that, but I think I could do this lab again, and I already know what I did wrong with this, but I'm gonna do it again and see if I can remember. Okay, so let's see what I gotta do. Okay, so count 2, launch Windows. What was it? IP config. Let's see what's going on here. Okay, we got the, then what? Answer questions 1 and 2. Okay, bet. So, IP address is dot. Bam. What'd you know about that? Chair set up right, you know what I'm saying? Subnet mask is this. Wait, what am I typing in? There we go. Okay. Now go to marketing 2. Oh, I almost got it. There we go. Find out the info of this guy, which is IP address is this 192.1.0. Okay, and the subnet mask is that. Yeah, okay. And then, okay, that's 3 and 4, okay. And now go to sales 2. Okay, so this is sales 2, okay. We're gonna ping. No, we were IP config. And then IP is that. Subnet mask. Okay, so they all got the same subnet mask. Okay, what do they want from us now? Now answer 7 through 9. Okay. Are these on the same network? So let's take a look at this. So it's the last octet. That's the one that's subnetted into different networks. So my guess first was that that leads me to believe that probably not. So let's calculate that all in my head, because why? Because half the weight of my because half of my weight when I step on the scale is due to my brain. That's why. So let's do it in my head. So we've got, so it's 224. So the okay, so that is the network ID, and then this is, but this is subnetted, so that's gonna be 224 is what? I think I'm gonna do the shortcut way, which is 256 minus 224. No, I don't even think that's even head math right there. Actually, for some people, but actually I'm kind of retarded, so actually I'm gonna do it the other way, which is bitwise way, starting from the left, which is 128 plus 64 is 128 plus 64 is 192. Okay, so it's not that. So then plus 32 is 224. Okay, so it's 123. So it's 3 bits. So 224 is the 3 bits for the host or for the network. So what is that? So 2 to the 3 is what we're trying to figure out. So 2 times 2 is 4, times 2 is 8. Is that what that is? 8? 8 subnets. That's to find out how many subnets. Yeah, 2 to the 3 is 8 subnets. So how many hosts per subnet is going to be 2 to the number of bits for hosts. So 8 bits total minus 3 bits for the thing is 5 bits left over for hosts. So 2 to the 5, I think it's 32 just because I remember that. 2 to the 5, because 2 times 2 is 4. Wait. How many bits? 2. Wait, 5. 2 to the 2. Okay, so 2 times 2 is 4 times 2 is 8 times 2 is 16 times 2 is 32. That's 5 bits. So 5, which is 32, minus 2 is 30. So 30. Hosts. Well, there's 32 for each, but only 30 usable. Okay. And then this one, what's the CIDR notation for it? The slash notation? that's counting how many. For the subnet mask. So it's 24, because it's 8, 16, 24, and then, whoa, and then 3. So it would be 27, but that's what I did last time, it's wrong. So what? Why'd you add? So that means it's the 5 left over? That don't make no sense. Or is it, hold on. It's 3, so it's 20. Trying to, how do I compute that? So 224, okay, I know it's 3 bits taken away from the 8 bits, which leaves 5 bits for hosts. So is it 32 minus 5? Is how many bits are total for? Because there's 32 total, minus 5 would be 27. Yeah, or it could be 24 plus 3. Has to be that, right? Because what did I try to do last time? 32 minus 3 is 29? I think it's 27, bro. Or else I'm totally tripped up. So it's 32 hosts because it's 2 to the 5 bits. So every 32. So this one is 1. This is another, because 32 plus 32 is going to be 64. So this guy's in the 64 one. 64 plus 32 is what, 96. This guy's in the same one as this guy. Wait, no. Wait, 32 plus 32 is 64 plus 30 is 94 plus 2 is 96. Yeah. So these guys are in the same one. Or no. This is 1 within the 32. And then from 32 to 64 is this guy. And then from 64, oh, they're all in different ones. So I'm just saying no. Okay. Now what's next? That was 7 through 9? Yeah, okay. Okay, so they want me to do something here. From marketing to ping sales to. Why is it not typing? No, cannot ping it. Answer question 10. Different networks. Yeah, because they're on different networks. Let's finish this lab and then we'll do the break. Or maybe we'll do the quiz and then the break. Oh, where am I? Where am I? Okay, now from sales 1 ping. Oh, dang, okay, I gotta go all the way. This guy? Ping who? Oh, those two guys. Ping both of them. Okay, bet. So lost. Nope, that didn't work. That worked. So what is this guy? Oh, they're in the same subnet. That's why. So this guy's misconfigured. Yeah, bet. Okay. Doing that. And then we're gonna do some routering. Now we want to connect, test. See if everything's working now. Who we pinging? Nice, that worked. And now we do the other guy. Nice, that worked. Answer question 12. Bam. Done? Scored. Give it to me. Let's go, baby. What did you think about that? What do you think about that? It's only 10 questions, so I just do it? Let's just do it. Let's just do it. And then we're gonna hit the break, bro. Oh shoot, I don't remember these, bro. I think it's this. That's a guess. Should I just check it right away? Let's do it. I got it right. Nice. It doesn't even say anything, okay, but I got it right. Lucky. Dang, I gotta memorize these classes, bro. One is... Okay. It's gonna be one of these two now already, because it's gotta be in order. That one is gonna be... Okay, so it's still those two, one of those two. 3 is also that. Nice. It's gonna be this. Nice. Let me just hide this because I don't want that up there. I don't want to see this either. Low-key. Did they even talk about that? I don't even think they did. Oh shoot, I think it's this one. Should you remember? Maybe those two. What is the new subnet mask? Okay, so when subnetting this net. Okay, so now this is where the rubber hits the road, baby. Let's make sure. Let's see if I got this actually. Okay, so those will remain because that's 16. And we want to support 12 subnets. So that one will be, how do you do it? It's gonna be in terms of twos, in terms of doublings, right? So it's gonna be 128 is gonna be 2, or 2, 4, 6, 8, wait, 2, 4, 8, 16. Okay, so 2, 4, 8, 16 is 4 bits. 4 bits. So that's going to be 128 plus 64 plus 32 plus 16. So 128 plus 64 is 192 plus 32 is 224 plus 16. So 224 plus 10 is 234 plus 6 is 240. So that's going to be 240. It's going to be 240. That's how good I am, baby. Now I'm going to check it to see if it's right because I know it's right. How do routers external to the network utilize CIDR? Oh shoot, I don't know, man. Actually, that one I don't know. Oh, I think it's that, actually. Wait, is that? It's one of these two. By using... No. Maybe this one? What does that stand for again? /16. Which subnet mask value would you use? Oh, that makes it easy. Thank you. This one. I think it does that. I don't know actually. Oh, it's not supernetting, it's complementary techniques. Is it this or this? I don't know. I don't know. Dang. Oof. I don't know if I passed this, bro. Let's see. I didn't. Oh, no. Because I got 3 wrong. Dang. How did I get 3 wrong? Let me see. Bro, that's crazy. I got that right. Okay. I got that right. Nice. Okay, that one was right. Nice. This one I got wrong. Oh, the documentation? Dang. It's that one? I didn't even know. Okay, so I tweaked on that. Okay, that's for multicasting. Okay. I got that one Oh, I got that one right. Nice, nice, nice. Big brain maths. This one, yeah, I got the CIDR wrong because... What? Or other summarized prefixes. How are you going to say it uses this one? I obviously thought it was not that because it could use also others. Oh, okay, that makes sense there. Yeah, whatever, bruv. This one, yeah, that was easy. Okay, this one. Yeah, that one I have no idea, bro. Okay, I gotta do that again, but hold up, let me go back to here, bro, because I don't know. Add that. This should be that. Oh, I see. Okay. So how do you do VLSM? So that's how you do it with this one. Okay. Let me just start this again, bro. Wait, this one and this one, bro. This one. This one. This one. This one. 12. Oh, this one. I don't know why it says /22 prefix, bro. It should just say it uses a prefix, not that specific one. look at this? Come on, now score that thing. Uh-oh. Yeah, what you thought about that? Bam. Finally, we can do this. Ooh. Wait, I gotta read cider, bro, because where are we gonna cider? Here. One, two, three, four. That's 22. Which would be 4, right? Because it would be /24/24/24/24. No, they've got 4 addresses in that range, so it would be 8, 16, and they have 4 there. So that's 6. So 4 bits. Wait, no, they have 4 subnets, so they want. Oh, okay, so I see how that works. So the exterior is that, so that way it's just 1 address. It'll translate that. What translates it internally then? Something like that. Okay. Let's just get this out of. I don't want to look at that anymore, bro. I don't want to look at that. Oh wait, now we get to do this. Okay. Boom. 15-minute break. Okay, we get a nice break now. Finally. So, I'm probably gonna go eat dinner because I'm really hungry. Let me at least just start this and then maybe leave in like 5-10 minutes. What session are we on, bro? 4? We might be able to hit 6, low key. Wait, can I bold it and do that? Oh, I can. Wow. Yo, that's what I'm talking about.
As part of troubleshooting, you might need to verify the IP configuration of a
It's kind of too long. I think I'll just bounce now. Alright, bounce now. Come back, finish up. Dang, that's crazy how I only got that whole entire time, 6 hours was just for subnetting, bro. That's crazy. But at least I kind of got an idea about it. I'm kind of okay with it. I can probably do this now and get into V6. Would be pretty cool to learn more about V6 because I really don't know too much about it. Maybe some troubleshooting with that. And there's the module quiz. Oh, I can finish. Oh, maybe we can finish this, bro. We can grind out hard. What does this look like? There's still gonna be almost 5 left, bruh. Alright. okay, fine, I'm here, okay, calm, settle down, everyone. Where are my slippers? Let's get it going, baby. Let's do it. Let's keep doing it.
Computer. The computer we're working on has a single network interface card. We can right-click the network icon, select Open Network and Internet Settings, select Change Adapter Options, select Ethernet, select Properties, Internet Protocol version 4, and select Properties. Here it says to get an IP address automatically. You can see that this doesn't give you much information. We can, however, close those property dialogs, right-click Ethernet, select Status, and click the Details link. Here we have the IP information from a DHCP server. Some of the lines of interest are the DHCP enabled, yes, the IP address and subnet mask, the default gateway, the DHCP server addresses, and the DNS server address. This dialog box isn't the only place that you can get that information. We'll open a command prompt and use the ipconfig utility. ipconfig displays some information. It gives the IP address, the subnet mask, and the default gateway. It's a quick and easy way to confirm that you have an IP address. We want more information than what we see here. We'll type CLS to clear the current screen. To get more information, we'll use the command ipconfig/all. Here's the information we want to look for. We have the line DHCP enabled. It says yes. We have auto configuration enabled, the IPv4 address information, the subnet mask, the default gateway, and the DHCP server. We have the DNS servers. One of the lines that we want to focus on for troubleshooting is this line right here, DHCP enabled. It tells us yes. Let's go back to the properties of this network interface card and make a few changes. Open properties. In this case, we'll give it static IP information. We'll configure a static IP address of 192.168.1.75. We'll leave the default subnet mask. We'll set up a default gateway of 192.168.1.1. This is the router. We'll provide a static DNS server address 192.168.1.10. Let's click OK and close these dialog boxes. We'll go back to the command prompt. We'll issue an ipconfig/all command and scroll up. Let's look at the differences. It says DHCP enabled and no. Before it said yes. We're no longer asking for information from the DHCP server. We have configured it statically. You'll see that here. The IPv4 address is now 192.168.1.75, along with the subnet mask and the default gateway that we statically configured. Notice that underneath the default gateway line, there is no DHCP server IP address line. We know that it's not looking for the DHCP server in this case. Let's go back to the network card and re-enable DHCP and DNS. We'll click Properties, Internet Protocol version 4, and select Obtain an IP address automatically. We'll also tell it to obtain a DNS server address automatically. Let's close these dialog boxes. Let's deactivate the DHCP server on the network. We'll switch to the server and deactivate the DHCP server on the network. It says the scope is active. Disabling the scope prevents clients. Deactivate the DHCP server on the network. These dialog boxes. Let's deactivate the DHCP server on the network. We'll switch to the server and deactivate the DHCP server on the network.
Yeah, he just jumped to it.
It says the scope is active. Disabling the scope prevents clients from obtaining IP addresses. Are we sure we want to disable the scope? We'll click yes. We'll return to the workstation. This time we want to use the utility called ipconfig/release. Now we've released any IP addresses. We no longer have an IP address that were given from the DHCP server. We'll enter the command ipconfig/renew. The computer is sending broadcast traffic to look for a DHCP server requesting an IP address. It might take a little time because it doesn't know that we shut down the DHCP service. This could take some time. We'll press Ctrl+C to cancel that. Typically, there would be a message stating it was unable to contact a DHCP server. We'll enter CLS to clear the screen once again. Let's look at an example scenario now. Say we have a computer user that says, hey, I can't connect to the internet. You go to the workstation and type the ipconfig/all command. We'll scroll up and start to diagnose the problem. We want to verify that DHCP is enabled so the computer wants to talk to the DHCP server. In this case, we're missing the line that says DHCP server with its IP address. Instead, we have an IP address assigned through auto configuration. This is known as automatic private IP addressing, APIPA. We know that because all addresses assigned through APIPA have the network address 169.254 with a subnet mask of 255.255.0.0. When you see that DHCP is enabled and you have an address within its range, you know that Apipa has assigned this IP address. This also means that if you have other computers on the network that couldn't reach the DHCP server, they have probably been given 169.254 IP addresses. Before we end this demonstration, let's go back into the server and activate the DHCP scope so the workstation can get an IP address. We're back on the server. We'll right-click the scope and select Activate. Now let's return to the workstation one final time. We'll enter ipconfig/renew. We have an IP address, but we want more information. We'll enter ipconfig/all. Scroll up and examine the information here. You can see that we do have DHCP enabled. We also have the IP address and the rest of the information that DHCP assigned to the workstation. That's it for this demo. In this demo, we used the ipconfig command on a Windows system.
Okay. Nice. Next. Keep it pushing, baby.
Over the last decade, there has been a shift away from interacting with interfaces using the ifconfig tool. The ifconfig tool has been replaced by the IP command, which has greater functionality and simplicity. In this demonstration, I'll show you a few ways you can interact with the Linux system using IP, and even show some of the corollary ifconfig commands. To start, let's look at how the interfaces on the system are configured. Using the IP address show command, I can see the two interfaces used by the system, the loopback device labeled LO and the Ethernet device labeled ENP1S0. The system uses the loopback device to communicate with itself. It isn't a physical device, it's virtual. We won't discuss it further. The other device is an actual device. Its name is a descriptor telling us something about the physical location. It is an Ethernet device, EN, it is on the bus number labeled P1, and it is in slot number 0, the first slot since it starts counting with 0, not 1. I'll use the old ifconfig command to compare how it displays interface information. Let's change the IP command to focus on just the ENP1S0 interface by typing IPAS ENP1S0. I've used shorthand options to make it simpler and faster to type. The A equals address or adder, and the S equals show. I'll also use the ifconfig ENP1S0 command for comparison. In the output for the IP command, we can see some of the settings, such as the IP address and network mask and CIDR notation /24. The MAC address is shown next to the words link/ether. Also included is the word dynamic, which specifies that this IP address was assigned by a DHCP or bootp server. The IPv6 address is also listed next to the string inet6. How does this information compare to what the old ifconfig command gave us? We see the IP address and the full net mask. We also see the IPv6 address and some other interface settings. We don't see anything to tell us whether the address was dynamically or statically assigned. So, if you're comfortable with ifconfig, why switch to the IP command? The answer is that the Linux networking stack has changed significantly since the ifconfig command originated. Those changes are frequently blind spots for ifconfig. When something is configured by the new way of managing networking, the ifconfig command might not see it. As an example, if you assign a second IP address to an interface, the ifconfig command might not recognize it. That's a simple example, but there are many more with varying levels of complexity. Let's temporarily add an IP address to a network interface by typing sudo IPA add 192.168.122.201/24 dev enp1s0. Now let's see how the interface looks by typing IPAS enp1s0. There's the extra address. I can also use the IP command to look at the connection or link to a network. Using the IP link command, I can tell an interface to start or stop receiving network traffic by typing IP link show, sudo IP link set enp1s0 down, and IP link set enp1s0 up. These show us the status, take the interface down, or put the interface back up. Note that the last two commands require root privileges, so the sudo command was used. I can also view and change routing with the IP command using iproute, or just IPR. This will list the routes on this system with the default route, or gateway, shown with the device and how the route was configured. This default route was set by DHCP. Let's add a new route with the IP command sudo iproute add 192.168.222.0/24. Let's see how that looks. IPR. There's our new entry. The IP command has much more to offer. You can create a network bridge with the IP command or an Ethernet bond with participating interfaces and mode. You can create, configure, and delete VLANs. And you can manage the ARP table or the neighbor table. That's it for this demo. There are many uses for the IP command when you're working with networking on a Linux system. An administrator can assign an IP address, change the network mask, add additional IP addresses, modify the route, create a VLAN, bridge or bond, and manage many other functions with this command. Practice and experience will help you become comfortable and capable using it.
Okay. We still going, baby. Ooh, let's go. You know how it be. You know how it be. Hops between Office 1 and Partner Corp. What was it? 102? It was. Wow, nice. Five? Oh, okay, now I gotta first hop. What is this? I'm like selecting it and it's not. Oh, it did? What? What is it? Is that what it is? I think that's what I remembered it being. Yes, sir. address of the external DNS server. There. There's two of them. Answer question. That was nothing. Well, there's two of them. Whoa, so much info. What is this? Oh, that's the whole thing. Huh? Oh, that's what I gotta type in. Oh, the way it's formatted is terrible, bruh. Oh my goodness, what? Here one. What even is this? I gotta type in this. What? That's all? How about IP link? Okay, I just picked one of them. Oh, okay, I did do it. Wait. Oh, wait, what? Hop 2 is that. Okay, and hop 3. Okay, no, I thought I typed it in wrong. Last router? How do I know which one's last router? There's only 3 options. I gotta look at the exhibit. Probably Partner Corp, no? Which is this? Which one is this? Probably a 12. That's what I'm gonna guess. No? It was this. How do you know? Oh, because it was just the last entry. That was just the gateway router then. Oh, yeah. smart. Wow. Dang it. I was a little too quick on that, bruh. I'm not smart. Oh, I'm not smart. Happens. What is this? Oh, this is the one I'm supposed to. Oops. Oh, no, I gotta do. Okay, fine. Okay. Now just type these in. 192.168.0.5, right? Yep. That is 198 dot. Oh, I typed something in wrong. What did I do? What? 6? How? It's 7. Yo, it's 7. It's literally 7. Yo. How is it 6? What? No way. Nuh-uh. Nuh-uh. How is it 6? It said 7. It literally said 7. One, two, three, 4, 5, 6, 7. Oh, between support? Yeah, support and... Seven. Is it -1, 6? Okay, 6 then. Okay. Oh, we got one more. it's got a V6. V6, IPv6. No, IPv4. Okay, there. Is it 4? So it's minus 1. 1, 2, 3, 4. It's 5. This is 1 hop. 2, 3, 4, 5. But last time it said 6. I don't know why. So I'm gonna just go with that. Connect to a Linux workstation. Oh, okay. Where's support? I don't like the way it's organized. That one sucks. The Windows one is better for sure. Ooh, well, let me try some. I gotta do some of these though. Now we want to ping bit. Oh wait, I forgot to do dash C, so that's good enough. Okay, that works. One, two, three, four, 5. They're both the same, bro. Basically. Look, 4 was 5, but I'm doing one less, so I'll do one less. 4. Linux machine here. I guess for your router. 1, 2, 3, 4, How's that 4 hops? Yo, somebody help me out with this. 1, 2, 3, 4, 5. Am I smoking on something? Skip this if we just start at the router. 1, 2, 3, 4. But why? Why would it do that? One is this one. 2, 3, 4, 5. It's literally 5, bro. Is that it? That's it. Now it wants to say 5? But that one says 4? How many hops? 5. How many hops? 5. And that one says 4. Yo, whoever made this is bugging. They're bugging. Yo, they're bugging hardcore. Now I gotta redo this, bro. These guys are bugging. I knew it was 5, so why are they bugging? Why are they bugging? So what do you want me to do with this now? Gotta redo all this? What do you want me to do here? IP config? And what I gotta answer? What's the IP address? This one. It's default gateway? That one. One, two, three, four, 5. 5. Rev. 5. Oh, I didn't do the other thing. Oh, what computer was I on? I forgot to do this. Is it gonna count? Yeah, nice. Okay, now I can go back to here. Now I can do what do you want me to do? Route. And ping it. And then trace route that. 1, 2, 3, 4, 5. Okay, 5. And now compare 1, 2, 3, 4, 5. It's 5 and it says 4. I don't know. I don't know, dude. I don't know. Score me that. Give me that 100, bro. Y'all are smoking on something. Questions. Let's give me this, baby. Come on now. Oh shoot. Dash S link. Report interface statistics, I think. IP dash S for statistics and then the link. I don't know. I don't remember. Or dig. Probably that one, no? What? Dynamic learning? Uh-oh. Not that one. Maybe this one? I don't know, dude. It was this one? Why are you talking about MAC addresses? This one. TTL, time to live, encryption level of the packet, no. Speed of the network connection, no. The packet's payload size, no. Number of hops it took for the packet to reach its destination. Time to live. No. What? Oh, maybe. was counting the things. I think I got 90. Or 10? 9 out of 10? I think I got one wrong. Yeah, which one? The gateway information on a Linux server. Oh, I tweaked. Oh, how did I not notice that, bro? Oh, that was so easy too, and I know it. I knew the answer to that too. That's crazy. That was just an L. Can I finally check off something here? No. Yes. Oh man, finally. Oh, I still got 2 more of those things. Bro, these are not looking good for me today. It's because of the subnetting though. It's just because of the subnetting. That really took a long time. Oh, these got a lot of pages, bro. That's crazy. Okay, let's do it. Oh, wait. This is a whole, oh, bet we get a whole entire thing like that. What you know about it? What you know about it?
IPv6 uses a 128-bit address that's comprised of 8 16-bit blocks, each containing 4 hexadecimal numbers. Each block is separated by a colon. With IPv6 being a 128-bit address, that gives us 2 to the 128th power, or approximately 340 undecillion available IPv6 addresses. Now, these are a bit more complicated than the traditional IPv4.
How do can I move this? I can. Whoa. I don't know why that moved. So, oh, I can just click anywhere. Here. Nice. Is that gonna come up to the 128? No, it's just 3.4 e to the 38. Okay.
Addresses we're used to. Thankfully though, there are some rules we can use to simplify things. Let's look at how we can use these rules to our advantage. In most cases, an IPv6 address has one or more blocks that consist of all zeros. When this is the case, we can remove any consecutive blocks of zeros and replace them with a double colon. But this can only be done once per IP address. In most cases, let's look at how we can use these rules. In most cases, an IPv6 address has one or more blocks that consist of all zeros. When this is the case, we can remove any consecutive blocks of zeros and replace them with a double colon. But this can only be done once per IP address, and the blocks of zeros need to follow each other. So even though we could have removed this block, it was more advantageous to simplify 2 blocks instead of just 1. The next rule is that we can remove the leading zeros from any block, but only if they're at the beginning. Any other zeros have to stay where they are. This also means that if a block has all zeros, we have to leave 1 0 if the block wasn't eliminated using the first rule. This leaves us with this simplified IPv6 address that's easier to read and work with. Now that you know how to simplify an IPv6 address, let's look at the different parts that make up this addressing standard. An IPv6 address is divided into 2 parts right down the middle. The left part is known as the prefix, while the right part is the interface ID, also known as a token. The prefix can be compared to the network ID in an IPv4 address, while the interface ID is comparable to the host ID. The prefix can be broken down into different components as well. The first 48 bits of the address is defined as the site prefix. The site prefix defines the location and is assigned by the local internet service provider, or ISP. The next 16 bits are the subnet ID. This is the equivalent of the subnet mask in an IPv4 address and tells us which network we're connected to. As mentioned earlier, the last 64 bits in an IPv6 address is the interface ID. This is a unique identifier we use to define the host. This ID is either automatically configured from the interface's MAC address or manually configured by a person. When the MAC address is used, the interface ID is considered to be in a EUI64 format.
Okay. Bro, we didn't do any standing sessions, bro. This is what I'm talking about. What'd you know about that? And give me some water too. This is what I was missing earlier in the day, bro. Come on now. Gotta get them standing sessions in. Take them breaks, baby. Take them breaks. I'll do the next session standing up, bro. You know what I'm saying? I feel like my screen got more red since I took this break. Oh, that's right. You all can see the redness, though. Y'all can't see this. Doesn't record that. Doesn't record that dang red. I like how I just stopped in the middle of the word. I was like, I'm taking this break. It's not even a word. Undecillion. It is a word, bro. I didn't even recognize that word. It's such a big number. 340 undecillion. That's crazy. Two or three elements? What do you mean, two or three? consists of 2 or 3 elements. The main header, oh, okay, I see. Like that, but that's the way it is for some reason, so I will just do that. Oh, you can do that? Nice. Oh, it's gonna have to be the whole thing, though. That's fine. We can do that. That works. Yeah, that works. What do you mean it's unclear? Well, it's not this one. It would be both, which means, but it isn't both. So that's why you can't do it, because it's not too. You don't do it because it's not because it's unclear. You do it because it's not two meeting zeros, right? You can compress this, but you can't compress a single. It would have to be, this one would also have to be all zeros. I'm not following. One contiguous series of zeros can be replaced by a double colon. So this can be replaced by double colon. No, it's both of them. Contiguous series. 1, 2 can be replaced by double colon. They're just not explaining it right. Just gonna say can only use double colon once. I did not know that. How do you say this? Format? Hold on, interface IDs. Interesting. Oh, what the? Okay, we can delete this then. Probably have to combine it anyway. Bam. You know what I'm saying?
In this demonstration, we're going to practice assigning IPv6 addresses to assign IPv6 addresses to this Windows Server system and a Windows Workstation. We're going to practice assigning IPv6 addresses to network hosts. Specifically, we're going to assign IPv6 addresses to this Windows Server system and a Windows Workstation. If you take a look at the configuration of the server, you'll notice that I have one Ethernet interface installed, and that's the interface we're going to work with today. As you can see, the IPv6 enabled basically means that IPv6 is loaded, but it's really not doing anything. So what we need to do is go in and manually configure it. Let's start by configuring IPv6 on the interface right here. I'll click this link, and we want to modify Ethernet. Right-click on it and go to Properties, and we'll go to IPv6. Select Properties again. Notice that it's configured to get an IPv6 address automatically, so let's change that. What we're going to do is statically assign it an IPv6 unique local address, which is really the equivalent of a private IP address in IPv4. Unique local IPv6 addresses always start with FC00, so that's what we'll begin with. Then we'll fill out the rest of the network address. Because this is a unique local network, we can actually do whatever we want. With unique local addresses, it's advised that they also be globally unique, but not required. This means, in theory, it's the only IP address used anywhere, including the internet. We're just going to make one up here, so let's enter FC00:, then 1234: for the second quartet, 5678: for the third quartet, and for the fourth quartet, we'll round out the network portion of our address. We'll do ABCD. We can put 2 colons in, followed by the host portion of the address, which is just 1. Remember, if we use 2 colons in a row, it basically says everything between here and here is a 0. So instead of typing out a long string of zeros, we're just going to do a double colon. That tells the system, hey, see these 2 colons? Just fill it in with a bunch of zeros. We need to fill in our subnet prefix length. By convention, IPv6 addresses use 64-bit subnet masks, so put 64 here. You can use longer ones if you want to, but the general convention is to use 64. We don't actually have a router on this network, but let's pretend I do, and it has the IPv6 address of FC00:1234:5678:ABCD:100. We also need to enter the IP address of the DNS server. I didn't tell you earlier, but this server is also our DNS server. It provides name resolution services for the clients on this private network segment. We're just going to use it as the DNS server address, so I'll copy and paste the same address down here under Preferred DNS Server. And then we'll click OK, and then click Close. At this point, we've assigned a static IPv6 address to this network interface. Let's take a look at what this looks like in ipconfig. We'll open up a command prompt, and we'll type ipconfig. So let's look at the network adapter. Here is the static IPv6 address we statically assigned. It's host number 1. Notice, however, that there is a second IPv6 address, a link local IPv6 address. You might be scratching your head and saying, why are there 2 IPv6 addresses assigned? Notice that this is a link local IPv6 address, while this, that we configured manually, was a unique local IPv6 address. A link local IPv6 address is required for all IPv6 addresses. If you enable the IPv6 protocol on any interface, you're automatically going to see at least one IPv6 address, even if you don't configure anything else. That'll be the link local address. Then, if you configure an IPv6 address or get one dynamically, you'll automatically have 2 IPv6 addresses. The link local IPv6 address is automatically assigned for you. It's used for IPv6 functions such as the Neighbor Discovery Protocol. You don't have to do anything with it, you don't have to manage it. Let the IPv6 protocol stack take care of that for you, and instead, focus on the IPv6 up here that you're actually going to use for inter-network communications, because link local addresses are just what their name implies. They're only valid on the local subnet. They can't be routed between networks. Basically, they're used for inter-subnet communications between network devices. You assign an IPv6 address to a Windows workstation in pretty much the same way as you assign it to a Windows server. So go down here, right-click on our network icon, select Open Network and Sharing Center, select Ethernet, and then we need to access the properties right here. Internet Protocol version 6, and finally, properties. So just as before, it's configured by default to automatically give an IPv6 address. Let's go ahead and statically assign one. As we talked about earlier, the IPv6 address that we're going to specify here has to be on the same subnet as the rest of our devices. Because we're using a unique local addressing scheme, we begin with FC00:. Then we have to provide the subnet address, which again must be the same as the inside interface of the router, 1234:5678:ABCD. We'll enter : again to specify that everything between here is zeros. We'll give it a host address of 2, and we'll use the default prefix subnet length of 64 bits. Once again, we'll enter our gateway, so I'll just copy and paste this in here and change the host at the end to 100. Now we have to configure the IP address of our DNS server. I'll paste this in once again and change the host at the end to a 1, which is my DNS server. Now hit OK and close out all of these. Let's go over here and open a command window. Let's look at our IP configuration using the ipconfig command. Here's our IPv6 address. We check it out and it looks like it's on the same subnet as the interface of our server, so we should be good to go there. We have a link local IPv6 address that was automatically assigned for us. We have our IPv6 default gateway defined, and it's on the same subnet as our host address, so we should be good there. Now let's do an ipconfig/all. We should see that the IPv6 DNS server is also set to that same address, and it is. Let's switch over to our DNS server and look at our records there. Okay, we're now on our DNS server. We'll go to Tools and then DNS. And we'll expand these out. You'll notice that in addition to our A records, which is what we used with IPv4, we now have an AAAA, or Quad A record, which is used for IPv6 hosts in DNS. Also notice that a Quad A record was created for our workstation because it's a member on my Active Directory domain. As soon as I update its IP addressing information, the appropriate changes were made to the DNS server. Here's the IPv6 address that we created for it. You can manually add a Quad A host address as well. We'll go up here and select New Host. There's a workstation that's on my network. Let's create a new Quad A record for it. It's called Linux 1. The FQDN, or the fully qualified domain name, is linux1.corpnet.xyz. Its IPv6 address is FC00:1234:5678:ABCD:5. Select Add Host. Now we have a record for Linux 1. Let's go back to our CorpNet PC1 workstation. Let's practice using some IPv6 utilities. Just as with IPv4, you can use the ping utility with IPv6, but you have to tell it that you're using an IPv6 address because by default, ping wants to work with IPv4 addresses. To do this, we add a -6 option, and then we specify the IPv6 address that we want to ping. Let's try pinging the network interface of our DNS server. Ping -6 FC00:1234:5678:ABCD:1. We're getting a response via IPv6 from the DNS server. Let's clear the screen. You can also use the NSLOOKUP utility because, remember, there were IPv6 host records created in our DNS server for the various hosts on this network. Let's try resolving the IPv6 address for our DNS server, which is CorpNet DHCP server. Let's type NSLOOKUP CorpNet DHCP. Press Enter, and you can see that it resolves the IPv6 address along with the IPv4 address. That's it for this demonstration. In this demo, we practiced working with IPv6 addressing. First, we set up IPv6 addresses on a Windows server. Then, we set up IPv6 addressing on a Windows workstation. Then, we used the ping and NSLOOKUP utilities to make sure that our IPv6 addressing scheme was working properly.
I think that's it. That's it for today. 10 o'clock. Time for bed, baby. Don't fall asleep. Let's see what we did. That's okay though. We had to get through that subnetting, man. We had to do that. We had to spend the time. Had to spend the time to do that. We get 6 of those. Nah, this is the 4th. This is the 4th. I thought this was the 5th. Maybe they didn't count one or something, bro. Because yeah, I think it missed one because how is it 10 hours and only 4? Yeah, I also don't. I'm miscounting these or something. Or I had it paused or something. I don't know, because I'm not tracking those right. Oh man. At least I got these done. We're getting there. We were supposed to be done with this, bro. I don't like the addressing stuff, bro. Addressing stuff kind of sucks, but you gotta know it. You gotta know it. What else? That's it. Oh wait, no, we gotta do. We gotta set up this. So what would we do again?